Hello, everyone. Welcome to the first VOLI workshop on visual object-oriented learning means interaction, discovery, representation, and applications. I'm Kaichun, the chair of the workshop. I just recently graduated from Stanford, and I'm currently a research scientist at NVIDIA. Today, I'm very excited to be here hosting this virtual full-day workshop together with another workshop organizer, Jiayuan from UC San Diego. So on behalf of all organizers of the workshop, I want to warmly welcome all of you to join us today. So yeah, I will give a very short, brief introduction to the topic of the workshop. So we interact with extremely diverse range of objects around us every day. And as human beings, we often spend little or no efforts detecting, understanding, and manipulating with these objects. We understand the rich semantics and functionality of the objects, so we know how to interact with them. Well, reversely, when we are unsure about some object semantics, we can just try to interact with it to get more information. So when the objects meets the interactions, on one hand, we want to learn visual representation of the object for downstream interaction. So we may want to learn the segmentation of an object, the 3D geometry of it, the part semantics, or the manipulation affordance, or other geometric, semantic, or functional information of the objects, just for the downstream interaction tasks. Well, on the other hand, using interaction can sometimes tell us more information about the objects. So for example, one can just quickly scribble on the image for a smart image segmentation algorithm to figure out the foreground object. One may also segment out the object in a scene by leveraging the local proximity of objects, object interactions, and the object motions. Or one can just directly interact with the object to query more semantic information, like the articulated part as shown in this example. So in this VOLI workshop, we study how to learn visual object-oriented representations from interaction and for interaction. The topics include how to discover and define the objects. So do we want to use supervised learning, semi-supervised learning, or maybe using purely unsupervised or self-supervision is enough? How to learn the object representation and what are the good representations. So what are the attributes that we want to learn and how to learn them from and for interaction. And finally, how to learn object-oriented representations for different downstream tasks in vision, graphics, robotics, and so on. So do we need to learn different representations for different tasks, or there might exist some unified representations that are good for all the tasks? So these are some topics that we'll be covering today. Okay, so here is the schedule for this full-day VOLI workshop. We will be hosting 6 speakers in the morning sessions. Each of them will deliver a 30-minute keynote talk on their most recent research works. And then in the afternoon, we will be hearing from 5 more speakers sharing with us their latest research. In the afternoon session, we will also have 2 sessions for the accepted papers. One is for the spotlight talks, and the other is a virtual poster session. And finally, we will end this workshop with a panel discussion. So for the keynote talks, we have 11 speakers in total. So 7 of them will be giving us the presentation live. So please do not hesitate to ask questions. So please leave your questions in the chat box of the ECCV platform. We will be monitoring that and forward your questions to our speaker. At the very end of the workshop, Yan Chao and Shu Ban, 2 of the workshop organizers, will be hosting 5 of our speakers in the final 40-minute panel discussion. So our panelists will be discussing some shared challenges, debating on some controversial topics, and sharing their unique perspectives for the next steps to do in this field. There will also be 2 sessions for the accepted papers. So the first one is right after the lunch around 1 p.m. We will play short spotlight videos for the accepted papers. And then there will be a 30-minute long poster session around 3 p.m. And this will be hosted in Gathertown. I will pass the floor to Jiayuan, so who will talk about how to log into the Gathertown and how to enjoy the poster session. So I will stop sharing and take it, Jiayuan.
Okay. Yeah, hi everyone, my name is Jiayuan, and Kaichun, let me know if the screen is not shared.
Yeah, I can see you.
Okay. So now I will briefly introduce like how to log in to the poster session at the Gathertown. So for the overview, the poster session will be held from the 3:10 p.m. to 3:40 p.m. The poster session will be held at the Gathertown, and the link is already posted on the workshop website. And note that please refer to our workshop website for the paper ID to choose the paper you're interested in. And first time, if you have not registered the Gathertown, you need to grant the access to the camera and the microphone to communicate with others. And then you can edit your username, here, you edit any name you want here, and then you can test your camera and the microphone. Then you press the join the gathering button and enter this platform. It will first show you a tutorial, so you can choose to go through this tutorial or skip that. And in this session, you can walk around the virtual room, and you can press X to interact with the object to see the poster. And when you stand by the poster, you can see the title and their PDF links as well. If you want to find the paper information, you can go to the center of the virtual space. There is a paper directory you can check. And for the presenter, also for the audience, when you are in the same space, then you can communicate with your microphone as well as your camera message, and the presenter can share the screen to show their work. Okay, thanks. And I will stop share and return it to Kaichun.
Okay, thanks, Jiayuan. So I think we can get started with our first speaker. I already see Kostas here. Yeah, thanks for joining the Zoom so early. Yeah, so maybe you can try to share your screen while I give you a short introduction. Yeah, so our first speaker is Kostas Daniilidis. So Kostas is a professor at the Computer and Information Science Department at the University of Pennsylvania. He obtained his PhD degree in computer science from the University of Karlsruhe in 1992. He has made a lot of important contributions to visual odometry, omnidirectional vision, 3D pose estimation, 3D registration, hand-eye calibration, structure from motion, and image matching. More recently, his main research interests focus on deep learning of 3D representations, data association, event-based camera, semantic localization and mapping, and vision-based manipulation. And today we'll be hearing from Kostas on equivariance from objects to scenes. Take it, Kostas.
Do you see the main slide?
Yes, I can see it.
Great. Thank you so much for inviting me, Kaichun, and all organizers to this workshop. I'm really humbled by the array of speakers that are following me. And it really looks as it will be a very interesting day. I am in my hotel here in Tel Aviv, and I will talk about equivariance and how can we make inference in scenes by applying equivariance principles only on learning single objects. This is work by my students Evangelos and Stefanos in collaboration with my colleague from the Wharton School, Edgar Dobriban. Let me start with a few basics. In traditional convolutional neural networks, as we know them for the last 10 years, at least after the deep learning revolution, they are traditional convolutional neural networks are translation equivariant by definition, subject to like discretization effects. But when one applies simple two-dimensional rotations, then these CNNs are not rotation equivariant. This video is from Daniel Worrell's presentation of harmonic networks 5 years ago, and you can see that when the input image is rotated, then the content of this window does not remain the same as it should be. So when we apply basic tasks like semantic segmentation without making our network equivariant, in the left case it is really equivariance in SO3 on the spherical image segmentation, then we see that the semantic segmentation completely fails here on the bottom. And also, if you have a classification task, this is from a paper called Strike with a Pose from 3 years ago, then you can really fool your classifier by drastically changing the pose. Some of these poses are really not realistic, but some of them, like the bus here or the fire truck, can indeed happen in reality. So how we define equivariance, let me present here the case of SO3 acting on the sphere, and the function being like a spherical image. We define equivariant map as a map that really commutes with the group action itself, which means if we take the input and we rotate it, and we write it here as lambda g, because this is really a warping operator of the whole image, and then we extract features. For example, it can be it can yield like a vector of all classes, like a softmax output for every pixel. Then this result is really predictable by applying this feature map on the original image and then just warping the feature map. And this makes this map equivariant. Now, equivariance could be achieved even with data augmentation by really using enforcing these commutation relations on the features by a loss function at the feature level. But we are interested in this talk is really equivariance by design, which means that we pretty much train only on like the unit elements of the group, like non-rotated images, and we want any task, whether it is segmentation or classification or reconstruction, to perform equally well on transformed images of the input without presenting our network during training with these transformed inputs. I will not go so much else into the basics, but I really want to advertise this a really amazing set of lecture by Eric Beckers from the University of Amsterdam. Eric has really the best introduction by far on group equivariance, whether it is about convolutions or attention, with really an excellent explanation of the underlying mathematics, and particularly of the representation theory needed, which used also in this talk. So in the past, my group and others have extensively worked on 3D object classification by applying spherical neural networks. So taking the mesh, not the point cloud, we defined a sphere that represents the object. For example, the value of the spherical function can be the distance of a point from the centroid. And we can add other scalar fields. For example, the angle of the normal to this distance. And then if we apply spherical convolution, which we actually implement in the spectral domain using spherical harmonics, then we see that the corresponding features are rotating here as the input. And if one wants to solve the classification problem, then by pooling, either average pooling or max pooling, you can really construct a vector here, which you see while the input is moving, this vector really remains invariant, and you can use it with a very simple classifier. Now, when the input is, for example, the value of the distance from the centroid, plus, for example, the normal to the surface, like it is here, if we apply the traditional spherical convolution, then we see that the vectors are not rotating together, actually, with a scalar field. This means that this prompted us, and this was really work by Taco Quer and Morris Weiler originally, that we have to address not only scalar fields, but also higher order fields. And later this was generalized also to the tensor field network by Tess Schmidt and her co-authors. And in our work, we applied it for the very special case of the sphere, where we used the spin-weighted spherical harmonics. And if you see in that case that the vectors are really rotating beautifully together, actually, with the scalar spherical image. So for many years, we had argued that pretty much convolution is all you need, in particularly group convolution, the same way that we are saying that any translational convolution system can be is translation equivariant. So any group convolution, it would be actually equivariant to the particular group. But we have to deal with other inputs, like sets, with like a set of points, where the first, very basically, the number of the input points is varying. And really, we don't have any regular sampling in order to represent it as a function. So in that case, we seek other actual architectures, and in order really to complete tasks like classification or reconstruction. And in this talk, I'm going to talk about 3D reconstruction from point Klaus. This is a task. The task of 3D reconstruction is by inputting a sparse point cloud. How can you get an output surface? And the dominant approach during the last few years has been to compute an occupancy function out of this input network. Alternatively, one can compute an SDF, where we map from XYZ to an occupancy value from 0 to 1. So I will present two approaches which are related to ours. One, because it applies local operations, and this is really the convolutional occupancy network, which takes an input point cloud, feeds it through a point net, where you get local representations. And these local representations, you can aggregate them either onto two-dimensional feature planes or directly to three-dimensional feature volumes. Then you apply a unit, and then at the end, out of this unit, you can use it to input into what we call coordinate-based network, where when we have a query point Q and we want to compute the occupancy value of Q, then we take into consideration as conditional. This network is conditioned on the neighborhood feature vectors. This was 2 years ago at ECCV, and 1 year ago at ICCV, the group from Stanford presented us really with the first equivariant, like point cloud encoder and reconstruction. They also presented classification. where the equivariance is achieved by enforcing all our features to have the dimension of the channels times 3. This way, any group action can be really post-multiplied on the feature vectors. And this way, by continuous, if you really are having a linear, really actually operation, then the post-multiplication with the rotation is not affected. So by construction, it becomes equivariant. And then the remaining problem is the nonlinearity, which is achieved by building an invariant input to our occupancy network. And this work, we have several now like extensions in recent CVPR and in the ECCV, including an approach that really uses graph embeddings and convolution to achieve the 3D reconstruction that will be presented in the main conference here, and was it came really concurrently with our work. So why do we want a C3 equivariance in 3D reconstructions? The reason is really the title of my talk. I said from objects to scenes. When we have a scene with multiple objects, we really don't want to really train train the network on scenes. We want the network to be trained only on objects. And this is not only a problem of on the variation of like the semantic content of the scene. It is also that if we want to apply equivariance and we will use augmentations for the scenes, then we would have a combinatorial explosion for any possible relative position and orientation between the objects. So what we really want is to train on single objects like the ShapeNet, and be able to test directly on a scene and getting these beautiful reconstructions that are really here extracted by the approach I'm going to present. So there is a practical really need, not only in terms of avoiding augmentation, but really in terms of not wanting to train on scenes. And so that every object can be reconstructed independent both of orientation and independent of position. And we also want this to be an approach which is also sample efficient, which means avoiding like MLPs, using really local neighborhoods and weight sharing, so that we have much fewer parameters, and also we need a much lower number of samples. So we lower the sample complexity. So to summarize, we really design local kernels that learn to reconstruct surfaces. And in the case of the scenes, this is independent of number of objects and the relative poses in the scene. So let me start with what is an equivariant occupancy field. An equivariant occupancy field satisfies also a commutation relation, and we are going to call this pretty much the decoder in our case, that if we have an occupancy network, which is usually a coordinate-based network, if we transform the point cloud, we want also the occupancy function to be transformed accordingly. And you can write it this way. We put the x as the condition here, that the occupancy function is conditioned on the input point cloud x, and compute the query q. If both the input x is transformed by a C3 and also the query, we want the function to remain the same. Depending on how you write it, this can be written in an invariant or equivariant way. And we want also to be able to generalize cross objects, like even novel objects. So we want to build priors from the objects. So we use an encoder F, which encoder F also satisfies this commutation that it commutes with the three-dimensional with rigid transformation. While this occupancy field is scalar, we want both the encoder and the decoder, the coordinate-based network, to be higher order fields, because higher order fields are much more expressive. So not being just scalars, but like vectors, matrices, and more general, like tensors. So to satisfy all these properties, we propose the first SE3 transformer for shape reconstruction. So I will first present the whole architecture, and then I will go into the details of every component. So we have an input point cloud, and this input point cloud is presented into a self-attention network with 10 heads. And here it goes the self-attention, the key, the value, and the query are all the same. And I'm going to explain how they look like. This extracts, this encoder extracts point features for every point, where we keep also the XYZ position. And when we want to compute the occupancy of the query Q, we take a neighborhood, the closest K points, and we take the feature of this neighborhood, and this is the query in a cross-attention network where the query is this query features, the neighborhood of the point query, and the point features are the point features of the entire point cloud. And this is not like a ResNet-like block or an MLP. This is a full transformer for decoding, which I think is really new. So let me go into presenting the encoder and the decoder, and also why they are equivariant. So as usually, we have an attention. We have the attention weights being built from the query and the key points. And for those, we compute weights which are really depend not on the absolute coordinates, but on the difference between the coordinates, something that has been proposed first by Fuchs and others in the SE3 transformers. And when you see here, we have the neighborhood of the points. The neighborhood itself is equivariant. So even if when we rigidly transform an object, the K nearest neighbors remain the same. So the neighborhood itself is equivariant as well. And if we want it to not be translation equivariant, but also rotation equivariant, we want our weights that depend on the rotation of the difference between the point and its neighbors, the point I and its neighbors J. We want those to satisfy equivariance, where this is the raw field of the input channels, and this is the raw field of the output channel. And if you, in the regular attention, we really usually add the positional encoding. We don't want this positional encoding. Instead, as I already mentioned here, we use the difference between the vectors. And one can show, and this is also explained the basics are explained quite well also in Eric Becker's lectures, that we can construct these W matrices as a linear combination of these CJ matrices with coefficients that are learned with a very small MLP and depend on the difference between on the norm between the difference of the vectors in the neighborhood. So this matrix C is a weighted combination of spherical harmonics and the Klebs Gordon matrices, and these W matrices satisfy the equivariance constraints for a linear layer as we encounter it here in the computation of the attentional matrix. So if we rewrite the whole operator after multiplying with the value matrices, this looks like this. And this is because of the difference here of the vectors, this is translation equivariant. The neighborhood where we sum up is also invariant under transformations. And we just have to see whether it is equivariant to rotations. To see that it's equivariant to rotation, this is quite actually, you can take a picture actually. This slide, I'm not gonna go over the whole thing. But you can see for all the value, the K and the key and the query matrices, we can prove that we have that row out of R times the weight matrix is equal to the W times the row in. Both of them, the reason we write this row, just to explain it shortly, is this row is equal to 1 if the F is scalar. But here, all the intermediate channels are higher than scalar tensors. They can be vectors, in which case we have the standard rotation representation, or it can be higher order values. Like one of them can be, for example, the vector of spherical harmonics, where we need the corresponding representation. And so we have rotation equivariance, we have the translation equivariance, and we have also permutation equivariance, because at no point really we just have actually only a summation across the points, and no really weighted linear combination. So if we show this more schematically, this is like for every neighborhood, we find the center CX. We compute the differences between this and the center, and then we attach these differences as a feature. And then we have this self-attention here, and this is cross-attention. If we apply this to so in the when we transform actually the input cloud, and we transform also the query, so that the query is transformed here, and the transformations, the encoded transformations are here transformed as well. In that case, they are transformed in as higher ordered tensors. So when we go from objects to scenes, this is an example, schematic example of two objects. Then we see that correspondingly all the objects are transformed based on any orientation of the object itself. And even if we rotate one of the objects separately, its features are transformed accordingly. So these are results on the single object reconstruction, and we present the classic equivariant test where we train only on the basic orientation of ShapeNet and train on upright objects. Here we train only on upright objects and test on the whole SO3 transformations, and here we train and test both on SO3. As expected, we see that our network is performing as the best when we train on a non-augmented, actually, a data set. But even if the data set is augmented in the training, then we still perform way better than the others, because we have a much more expressive network with a higher order tensor in between. So, and higher order representations. So when we present with a scene from sparse points, then we reconstruct each object from several objects in several orientations. We reconstruct each object as if it would be just by itself. While if we apply the occupancy network or the vector neural network or the convolutional occupancy network, then we really see the same like leaking of the surface we would see also in the leaking of the semantic segmentations. And we only anecdotally also run it on parts of one of the Matterport apartments here, like if you have worked on like object nav and or vision language navigation tasks, you know very well. Here is the scene around the table. Here is like the bed, and here is like the sofa with 2 armchairs and the table. So multiple objects in one scene, and all of them really reconstructed pretty well. So just to close with a take-home message, we really presented the first SE3 equivariant coordinate-based model that uses attention both the encoder and the decoder, like the actual coordinate-based network. And by enforcing only local features, we can reconstruct the scenes without estimating the object poses. We really don't need actually to train on the whole scenes at all. And the procedure we follow is just the training on ShapeNet and single objects on their like upright views and the canonical views, and reconstruct like both novel objects because we use priors and an encoder, and scenes consisting of multiple objects of arbitrary relative poses and orientations. And you can find our work on the archive. I think I am the 27 minutes, and I really thank you very much for your attention, and thanks for inviting me.
Thanks for the nice talk, Kostas. Checking the website for audience questions. Yeah, maybe let me start with the first question. So yeah, I think adding the equivariance to the neural network is quite important, but in your talk, it seems that you need to add some special designs where I'm not sure if those can be think of as some constraints, like you need to design some special neural layers to enable the equivariance of the neural nets. And do you think putting the special constraints will somehow decrease the network learning upper bound, like the power, compared to the regular neural networks?
That's an excellent question. That's really an excellent question, spot on. And this really differentiates work that is based on attentional architectures from like work like point convolutions, point-cloud convolutions, or the original tensor field network. When you try to use only like just a local convolution-like operations and not computing the attention matrix, then you remain with very few actually coefficients as unknowns in your W matrices. Your W matrices really have very few degrees of freedom, in particularly like when you have a difference between in the angular direction in the SO3. While here, I mean, the way we construct the matrices involved in attention, we really have a lot of freedom on learning these coefficients here of the weighted Klepsch-Gordon matrices. I think that was one of the reasons actually we decided for transformers, although we still actually work locally. We use a transformer, but we don't use the arguments from natural language processing that we can really reach long-term dependencies. We still use local neighborhoods. But yeah, this is a very good question. And indeed, for example, even on images, like on harmonic networks, very few coefficients to learn. You cannot make them very expressive. So the other way to increase the expressivity is although you have a very low order like inputs and outputs like scalar fields to all the intermediate layers to be like tensors. So which means that in the language of neural networks, having tensors as features, it means here that you are mixing the channels at every operation with like an equivariant. You're mixing them in an equivariant way.
Yeah, and how do you envision this type of network will also be applicable to other 3D tasks like detection, segmentation, yeah, other than reconstruction?
That's a very good. I mean, that's a very good question. I mean, we focused on the reconstruction because we put a lot of effort on the coordinate-based network, on the decoder, and we plan to apply it also on detection. I think in the case of the point clouds, we are very lucky that it's pretty much the SC3 transformation we consider. In the case of images, things are becoming much more, as many of us know, much more complicated. One of the reasons being that it's very difficult to model. Mathematically, we cannot really define an SC3 equivariance on the image because the content is really changing in the image.
Yeah, do you have some general advice to the audience? Like if some of the people want to put effort on adapting SC3 equivariant network to other tasks, like what are the pitfalls and the suggestions?
So that's very good. That's very good question. And many people are really hesitant because it requires a lot of effort as opposed to augmentation, which really actually you can just run a simulation and produce like thousands of augmented copies. But equivariant is really a matter of efficiency. I think it's very elegant. It is orthogonal to the scale-up philosophy of these days, but I think it is worth doing. For example, the AlphaFold, one of the most of the biggest successes of deep learning is based on an equivariant transformer on protein structure prediction. And if you have problems where you have a combinatorial explosion of the augmentation, like here on the scenes, the same is in the transformer. Actually, the amino acids are have relative transformations to each other, and you really have to having like in the human case, if you have 375 such like amino acids, you have to combine all possible rotations. The same thing here. I think data augmentation would be prohibitive if you had like 10, 20 objects. And in that case, you really have to use equivariant. We are very lucky. There is an excellent like library, E3NN, and by run by Tess Schmidt. And also, I really recommend people to see the lectures by Eric Beckers.
Yeah, hi, Kostas. Maybe I have one question to ask. Like since you use the equivariant network, it might somehow like ignore the rotation somehow in the encoder part. Like when you do some task that require maybe the relationship between like two objects, like I mean the relative rotation or other things. Well, as a fact, like maybe you can use like ensemble or other way, right? I mean, I would like to hear your opinion on that. Yeah.
No. This is actually what you said is invariance. Equivariance is the opposite. Equivariance makes the relative rotation estimation really extremely easy. Invariance makes the rotation disappear.
Oh, yeah. That's true.
So the equivariance, let me show here. So equivariance, an equivariant layer like the ones that are shown here. So this actually, if you have you just out of these vectors, you can really actually compute the rotation just like pretty much with like a higher dimensional Procrustes. So this is actually, it can be used also for relative pose estimation. But we argue the other way. We don't need to estimate pose if we want to do shape reconstruction.
Yeah, sure. Yeah. Yeah, thanks for the answer. Yeah.
Yeah, thanks, Kostas, and hope you enjoy the rest of
Yes,
ECCV,
thank you.
possibly in person, instead of online.
Yeah, it is wonderful here in Tel Aviv. Sorry guys that you're not here.
Yeah,
thank you very much for inviting me.
Yeah, so we need to proceed to the next speaker. I'm happy to introduce my collaborator. So I really enjoy my collaboration with Professor Niloy and Mitra. So Niloy is, maybe I introduce, we're already sharing the screen and I can see your slides. Yeah, so Niloy is a professor of geometry processing in the Department of Computer Science, University College London. He received his master and PhD degree in electrical engineering from Stanford under the guidance of Leonidas Gibas and Mark Lowe, and was a postdoc at the Technical University of Vienna. His research interests include shape analysis, data-driven geometry processing, structure-aware representations, abstractions to reason from raw images, videos, or scanned data, and many other applications in 3D vision and graphics. And today I'm quite excited to hearing from Niloy about interacting with neural assets.
Hello, thanks, Kaichun. Thanks for the organizers for inviting me. Can you confirm that you can see the main slide, the main view? Yeah.
Yes.
Good. Okay. So today I'll talk about a problem that we have been working for several years, earlier with classical representations, but lately of neural assets or neural representations. And I'll talk about the opportunities and the challenges here. Just proceed. So a task that we often need to do is the following, like we have observation of the world. So here we have, say, a video sequence or a set of inputs. So this is our old office building at UCL with people interacting. And we want to get an abstract understanding of the world for subsequent interactions. So by this understanding, I would like to get objects in context of humans and how they are relating or interacting with us, so that we get like a 4D reconstruction of space and time, right? So that's the grand goal we have. Now, with recent neural representations, and I'll talk about some aspects of them, we can often go from here to a photorealistic representation. But what we really care about, and I will talk about this as we go, is an understanding at the level of depth, segments, objects, and how we can capture and identify interactions across time. And it would relate to the equivariance discussion that happened earlier on in this session. So last year or earlier this year, this Behave data set was released, which is a super cool data set of humans interacting with the scenes. And the focus was on identifying SMPL models of humans and understanding contact point with the others, right? What we are going to talk about is a complementary problem, not the human. The focus is on the objects and how can we represent them and how can we represent their relation between their parts. So the essential question here is about representation. And this was the second bullet Kaichun has in its talk. And I think most of the problem that I'm interested in deals with representation. And one of the recent papers we had in this is this value field that we presented earlier this year at SIGGRAPH, where we investigate photorealistic reconstruction, but I'll make clear why we are interested in the context of this workshop. So as many of you know that with the advent of NERF a couple of years back, fast and realistic reconstructions are now possible. You can take a collection of images and create novel views, right? And this was a breakthrough a couple of years back with an ECCV paper that really has significantly affected the field, and there's multiple workshops running today on this very topic. Now, while it produces photorealistic effects, it has one problem, which is it takes long to train and also long to render. So these times are order of hours. So this is like usually the photorealistic results, you get 10, 15 hours per single scenes. In contrast, if we go back 20 years back in traditional graphics representations, like a voxel grid, we can get like in order of 10 seconds, a trained network. But the problem is the quality is not as good as we'd want, right? So we lose a significant quality. And although you're seeing this in over Zoom, even if you see in person, you still see that the quality is not good. We'll only hit 20 ps/hour or something about that. So here's where we stand. NERF gets very high quality photorealistic rendering, but takes orders of hours. But the traditional one is slow, is fast, but leads to poor results. So can we improve the situation? And to give a preview of what we are going to introduce, there's a very small change would result in very photorealistic results in very fast time, order of seconds, again, 10 seconds. So that's for training, and rendering is really fast, order of milliseconds. Okay. And to get to this destination, we need to understand what is the current problem. So let's do a little bit of background. It's good because we haven't talked about NERF yet. So let's quickly do a recap. So we have a collection of images. We call this posed images because they come with poses. So we optimize the NERF representation, and I will talk about this a little bit in the next slide. And once we have trained it, we can render from novel views. Okay. Now, in the core block, which is optimization, what is really being learned is at each location, we are learning two functions. A transparency function, which is a sigma, and a color value, which is RGB. And occupancy net that Kostas talked about in the previous talk is only the occupancy. Here you can do occupancy and color. And the interesting thing, this can be optimized end to end via the volume rendering equation. Now, the core network is really a simple MLP that takes in location along with the view direction and outputs these 5 numbers. So how does the volume rendering step work? And since this is a vision conference, I'll just quickly go through this. So we have a volumetric scene. We have a ray cast through that. We sample that ray. And at each location, we are really aggregating how much light goes through and what color or emittance this is. So this is the sigma value, and this is the color value. These are the green and the blue colored arrow. These point to what the network outputs. And then we have the step size, which is the delta, which is a parameter. So all this is good. And this can be optimized, but it is slow. The other thing which I will get to is it's a global representation. That means when you have the subsequent tasks very hard, like we are interested in understanding interactions or doing generative models, etc. So if you go back to the traditional voxel grid representation, it's really not much to say. It's voxel grid, and that's all. But how can we adapt it in the context of radiance fields? We can represent the global MLP by a grid-based representation, where at each grid location, we again store the density and appearance, the sigma and RGB. Right? But now we are storing again in spherical harmonics. Against the justifications of this has already been discussed in the previous lecture. I'll leave that. And if we do that, we get representation which are good, almost there, but still quite blurry and not quite photorealistic. But one thing we have achieved in the goal is it's a local representation. So why is it blurry? It's really easy to see once we go through the details. So what really happens is we have locations, any arbitrary grid location, and we take the nearby features or colors or density. We just do a bilinear interpolation of this. Now, if you think through, this is only going to result in smooth signal inside the cells, which means it cannot represent discontinuities, and surface in some sense is a discontinuity, so we'll get blurred edges. So in comes ReLU fields, which is what we are proposing. It's really a single line change, so you have to watch carefully the real change. The real change is we do exactly like before, but instead of returning y, we need a nonlinear version of y, which is a ReLU field. And this results in us being able to capture discontinuities. So how is this happening? What really happens is now inside a single cell, following things happens. If all the cells have the same positive value, like the grid location, it's the same as bilinear interpolation. Nothing new happens. But when we have mix of signs, plus and minus, then we can start representing edges, because as soon as the interpolated value goes below 0, it would only output 0. So this allows the network an ability to represent discontinuities by allowing or handling negative values. So it allows it to optimize the negative value and thus capture discontinuities. These are the easy cases. It also gets its curve-like features. And that's pretty much all. So and the vector representation on top, so we can do it in stages, just like ReLU. And on the right, you can see very sharp results, just because it now has this power of capturing edges or sharp features. So if we revisit our problems, we can get very crisp results, as you see on the right. I hope you can see that through the Zoom one. Otherwise, please watch our the results on our webpage directly. And now the training time is the order of 10 minutes, but the render time is about 100 milliseconds. And this is in contrast to what we had before. So we have a very good PSNR right now. Now, this can also be applied beyond this to occupancy field that we show in the paper. As you can see here, the crispness, as you can see on these Lego fields, continue to be here, even at a coarser grid resolution. The other thing that would become relevant is now it's a local representation. It can be applied to real scenes with the background modeled as a separate MLP and then the ReLU field for the foreground object. Again, this can be done. So the limitation is we still have the n-cube memory complexity, and we'll discuss this in the second part of the talk, how we handle that. We cannot model more than a single crease in a voxel, which means either we need more higher order primitives or we have to have smaller cells. So really the take home message is a single line of code change can get us from the left to the right, which is quite surprising, but that is often a good thing to look at the actual implementation and find out where is the main capacity limitation of the network. In this case, the lack of the right nonlinearity at the right place. Beyond photorealistic reconstruction, now we have a local representation. So you can think of applying like a GAN on these ReLU field signals. This is a work we presented earlier this year at 3DB, where given a single scene, we can generate multiple variations of the same scene, as you will see here. This is only one, but you can generate many self-similar variations. And these are generated in 3D, so these are view consistent again. I'll show you one more time. So these are view consistent by construction, because it's what we are creating is this abstract 3D representation. So this brings to the second part of the talk, which is how can we take these implicit representations we have to go beyond single objects, which is the overfitting case, to allow us to go to more generalized setting. And this is work done with Connors and Gordon and Leo from Stanford. And this is going to be presented at NeurIPS later this year. So a paper that has long been of influence to me is a paper by Tom Funkhauser back in 2004, which is this idea that we can create new shapes by combining parts from many other shapes. And this is called modeling by example. Now, this has led to hundreds, if not many hundreds of papers subsequently. And the challenge in this problem is twofold. One is which parts to put together and how do we put together the parts. So when we put together the part, how do we connect them? And this is a problem we also work with Kaichun on the structure net and subsequent structure edit paper that we worked on. So if we revisit the problem with our new tools, we have the following thing that we are going to enable. We have the set of objects, in this case chairs, and we are going to have coarse primitives to edit the chairs. So the blue box are going to be stretched into the red box, right? So this is the edits given by the user, and we want to enable these edits while still preserving the uniqueness of the chair. So we still want the slats of the back chairs or the dents in the cushion as on the right. So how can this be enabled? So whereas beyond this editing, we can also do a modeling by example, where we now combine parts from different locations and put them together, right? And again, we want to have the uniqueness of the parts and still have the ensemble of the parts look correct. Here's another example, right? So that's where we want to go. And you can think of this being parts inside an object, but one can think of doing the same thing in a scene where the individual object becomes a part and the scene becomes an ensemble. And as you will see that this notion of equivariance also comes in, but here the equivariance would be how we construct the neural network in sort of how we structure the mix of information. So that's the goal we have. So what's our approach? Our approach is the following. We would have two networks, one network that is learned across shapes. So we'll use PartNet for that. So we'll use the PartNet dataset to learn something that captures chairness, and I'll talk about this. So this is our Neuform generalizable model. And then we would have a model overfitted to each object, which is an overfitted model. And the ReLU field is an example of an overfitted model. So if you look on the left one, the generalizable one, this looks like a chair, but we lost the uniqueness of the chair. On the right one, it's good in overfitting, but as soon as we start editing, the chair sort of falls apart because it only has seen a single chair. And what we would like to have is a Neuform that allows us to edit the chair, but still keep the uniqueness. Okay, so we want to combine the best of both worlds. Now, our biggest sort of insight in this work was the uniqueness of objects comes from the identity of the parts, right, which is nicely captured by overfitted models. And the uniqueness or the notion of chairness, for example, comes by the ensemble of the parts or how they are joined. So this is at the joint location. So that gives us an inroad to how to attack the problem, that we would like to get the joins from the generalizable one and the details from the overfitted one. But the main challenge now is how do we have two networks work separately and be able to combine them? And as we'll find out, this would be in the network architecture. So let's describe the generalizable prior. So if we just do an occupancy grid on the whole chair, this is just not going to be work because it's a global representation. So we want a local representation. So I'll explain this in stages. So what we would like to have is an overfitted prior that captures the input shape. So that's good. But this by itself is not going to be enough because as soon as I start editing, as I will show also later, the joints fall apart. Although the parts of the chair look good, but the edited part doesn't work because it has been trained on a single example. And the blending will allow us to clarify or remove these blemishes near the joint. So here's the architecture, and let's go into the details in the following slides. So an object is represented as an ensemble of parts, and each part is abstracted by a cuboid. And this is our motivation of structure-aware geometry processing, where each cuboid is a cuboid which is size, but also it has associated coordinate frame. And this is what we are going for the equivariance. So each of these colored boxes has an orientation that we would be using. So how is this going to be encoded? So we will sample points on these parts, right? And then we would have some PartNet-like representation for the point, some PointNet-like representation for the points. And then we would also have a latent code for each of the parts. So this is how it would work. So each of the boxes with the centroids and dimension goes through an MLP to give a latent code GI. And this latent code, this embedding is trained across all parts of partnet. And then the surface points, as we have in the bottom branch, these two are combined. The two latent codes, so GI coming for the latent code of the cuboids, individual cuboids, and ZI are the point codes. These together form a feature vector Fi, right? At this point, the Fi is aware of only the current primitive. It is not aware of the rest of the primitive. So how do we make it aware of the rest of the primitive? This is where, again, the transformer comes in. So we saw the notion of transformer for injecting information across its neighbor in the previous talk also. So for each pair of parts, there is a mixing network that would mix the part information. And then we will process the query in the query network to give a final occupancy. And the query network is the most interesting part here. So let's go to the mixing network. So for each of the pairs, it really goes through a transformer and gives output. And the F1 and F0 is 1 and 0 is a way to say that I am processing the ith primitive right now and not the jth primitive. The 0 means this is not being processed. And this is used in the query. So given these features along with the concatenated latent codes, each query now gets attention from these features. But the interesting thing that we do inside this attention block is this query is re-indexed in the local coordinate frame of the primitive. So this is where it's relative to the coordinate frame of each of the primitive box to get an HI star, similarly for HJ star. And these are aggregated in a permutation invariant way to give a final occupancy. So this by construction means that if the chair is rotated as a whole, everything would be equivariant by construction because everything is relative to the coordinate frames of the parts, right? So that's good. So with that block done, now what we can do is we can use the same architecture also for overfitting. And how we do this is we keep this the part in the shaded one fixed because we don't want to retrain it. We only train the attention layer to overfit to the individual examples. So this is another way of saying that there's 3 networks being learned. Really 2, the third one is blended. So the green one is the generalizable one with this local coordinate frame encoding. So that's a top branch. And each of the query part is aggregated by the big summation signal using some weighting coming from the attention layers. And the overfitted, as you see on the bottom one, this doesn't have a collection of parts. It's just like a single object. So that's all good. And then the green and the pink are blended to get the yellow one. And the blending is just like linear blending. So the main architectural choice here was to design the generalizable and the overfitted networks in a way so that we can directly blend in the space of weights and the space of network parameters. And that's really useful. And the blending happens spatially. As we get closer to the actual junctions, then the blending happens. Deep inside the junction, the generalizable model takes in. And away from the junction, the overfitted model takes in, right? So there's like a smooth transition between this. And that's all we need to do. At editing time, parts can be updated, which means corresponding part features inside the red box are updated. The part 4 features are frozen for the overfitted model away from the junction because we keep the identity of the individual networks. And the blending we already saw. So that's for the architecture, and now we are ready to see some results. So in terms of here are the ground truth, here are some competing methods. Koalas was last year, Spaghetti was this year's graph work. And as you see in ours, because we have this nice blending directly in the architecture, we can directly get crisp results away from the junctions, directly from the ground truth. And at the junction, this is where the generalizable networks are producing these values. Here's another set of things with more crazy shapes, as you will see, but it's not a problem for our case because the overfitted network has seen this crazy shape, so it can see the the details or the uniqueness coming from the object and still get nice crisp results at the end, while still having nice junctions, as you will see on the right one in the zoomed in sense. Editing is the most interesting part because now we can take parts in these cuboids and start playing with them. This is, you can see already the contrast with coalesce. I'll also show some results with spaghetti. That ours is the only one that does a good blend of keeping the uniqueness of the chair, again, the slats and the features on the backrest or the seat of the sofas, while still achieving the end goal of editing where the arms are raised or the arms are manipulated. Here's the corresponding results with spaghetti that struggles to preserve the uniqueness of the shapes. There's much more results here on the web page and on the paper. I'll leave you to look through this. You can go beyond chairs, of course, to any objects that are present in the partnet in sufficient models to get the generalizable one. The lampshade you see on the bottom left is quite a nice one because it shows that it can even keep the features of these collapsible structures for moving the head of the lamp. Quite a nice example for that one. It allows part mixing, as we saw before. So this is again goes back to the modeling by example paper, where we can take parts from different one, combine them, and again you can see that it keeps the uniqueness of the parts, which is good, but also fills in very plausible geometric connections because it can see these from the generalizable. These also reflect in terms of numbers, as you will see. That the overfitted numbers are very good. They should be because they're overfitting to the individual examples. But please remember that the overfitted numbers are for the original shapes. But as soon as we start editing, these numbers are not so good. And in contrast, the new form gets a nice balance between these two. So in summary, what we saw is the following two observations, that a local representation can indeed now be very quickly trained, right? And being local, it allows us to do local operations in the sense when we combine them, we can do it in the local coordinate frames. We can have features directly on grids, on cuboids connected to parts, etc. And these allows us to have a blend, or one of the first approaches that allows blending between this overfitting to single objects versus allowing the generalizability across models or across collections, and we can start getting the best of both worlds. So what we are now looking at is how to take these representations and go back to the interaction capture worlds, where we can go and start interacting these objects along with their surroundings, along with humans and other things. And there's a lot of exciting works to follow. I'll take this opportunity to quickly advertise our website, where you can see all the code and data. And also we have one PhD opening. So if you're interested to work in this topic, please get in touch. We have a position open that is being advertised right now. So with that, I'll stop here and take if there's any questions. Thank you.
Yeah, thank you for the talk, Niloy. Yeah, maybe I can first ask the question. Yeah, so like for the interaction, like in the real world, we have a lot of like articulated objects, like they consist of like different parts and their relationship, like the joint. I think it's something that you are modeling in your like second work. So I'm curious, like whether there exists some direction that you're exploring to try to like combine maybe nerve and articulated objects, like how we can build articulated objects, I mean, reconstruct the articulated objects in like implicit fields. Like, is it possible, like how we do that? Yeah.
So that's a really good question. And here's an early result of that type of work that you're asking for. So what I don't show here, because this is what we're currently working on, this is an object level representation, and the human is represented in terms of articulated parts. And you can imagine how this is, right? Now, we can do very similar to what we showed for Neuform, that we can have some latent code for the individual parts and let them move and have the articulation or a rig. If it's human body, you have like a skeleton rig, we can move with it. So this part works, right? But you ask for the challenge. The challenge is the following, that there is a much more subtle and important interaction going between the parts. So when I flex my hand, then the feature starts changing because my muscle bulge or not, right? Or when I hold the ball, the weight of the ball will influence the weight on the hand, etc. Right? So these things are very subtle to capture, but they are the most interesting ones to capture in the context of interaction. And that is, I think, the really difficult problem that we hope that we can make inroads to. And that's really a challenge. And it's also hard to capture these data, because when we have these sort of object level interaction at a very fine granularity, the vision systems would not even see it, because this happens under occlusion. So the challenge is, how do we bring in maybe human specific body muscle models and other things to capture these interactions. So.
Oh, yeah. I think there is a question from the audience, like, is there some ideas on like how to extract high quality mesh from the nerve representation?
This is a question that I think I would frame it a little bit differently. So there are applications where meshes are absolutely necessary, right? And one can discretize extract a mesh out of the inferred density field. So we had the Segravation work last year on differentiable triangulation that allows us to extract triangle meshes by jointly optimizing for the vertex position and triangulation. So it's not super robust, especially on noisy data, but it's possible. But I think it's worth thinking if it's really necessary, because as soon as we do this conversion, certain information gets lost. I think in my explanation, nerve works so well because it jointly represents geometry and material. As soon as we decouple it, we lose something. So unless it's necessary, I would avoid that step. That would be a slightly long answer for that question.
Yeah, so if I can follow up. Yeah, so if I can follow up upon that question, so I'm also interested in, like, so how do you think this nerve representation is better than mesh if we want to use them for downstream interaction? Like if we want robot to manipulate, so it's obvious that mesh is maybe easier because we can simulate.
I think mesh, that's a better way, that's a different way, but in some way I think it's better, in my opinion, of thinking that following interaction, that you directly interact with the mesh rather than doing another interact with the nerve representation rather than directly having a separate step. And that's what we try to do here. We don't do a discretization into a mesh, right? We directly work with the density field. And this is doable the more we get into the details of the algorithm, because to do the meshing, we need to have a binary decision on where the surface is versus not. And that's what the interaction uses. So if one can backprop through the interaction by staying with the implicit representation, and that would be the goal to have. But the challenge is we have to rethink all the nice priors we have about human bodies and other things, the SMPL models and others.
Yeah, I'm really looking forward to this new work. Yeah.
There is one more subtle thing that I do want to call out, because it's useful, that although nerve is very good for photorealistic, it does bake in many of the photorealistic effects, which may not be necessary, or is more like will act as a noise for interaction related tasks. So that's something we have to be aware of.
Yeah, I have one more question. So for the first part, like using the ReLU to make the more crisp edges. So yeah, there are also papers saying that using some sine or cosine functions, which might achieve the similar thing. So how do you compare to those works? And yeah, so do you think ReLU is the best nonlinear activation function? Have you tried the other ones?
We have tried other ones. It is not the best, right? But it is the simplest. So what we wanted to do is like, that's also in the title, what's the minimum change to do that in terms of cost, not in terms of code lines, in terms of cost, because that's useful. Because that tells us like what gives us the biggest information delta, right? So that was the goal. Of course, we can bring in more nonlinearity, and the more we go down that, we can eventually have small MLPs, large MLPs, or full scale MLPs to do that. But it's a question is, where is the crispness coming from, right? But, yeah. And you can do this in conjunction with positional encoding, which also brings in these sines and cosines.
Mm-hmm. Okay, thank you so much.
And on the right here is occupancy field result that I didn't talk about, but it can also be directly applied, but then you directly optimize for the geometry rather than the color. That's pretty obvious how to do.
Yeah, thank you so much, Niloy, and hope you enjoyed the rest of the ECCV.
Yeah. Thank you.
See you.
Bye.
Great to have you. Yeah, so let me move ahead to our next speaker, Judith Fan, which will be a pre-recorded talk. So let me first introduce Judith. So Judith is an assistant professor in the Department of Psychology at UC San Diego. Her research addresses questions at the intersection of cognitive science, computational neuroscience, and AI. Her goal in building computational models of such behaviors is to understand how perception, memory, motor planning, and social cognition functionally interact in the brain, leading to a more unified understanding of how multiple cognitive systems are coordinated during complex neural behaviors. And I believe, yeah, our technician can help us play the pre-recorded video of Judith Fan, where she will talk about Physion.
Hi, everyone, and thank you so much to the organizers of this wonderful workshop for the kind invitation to speak today. My name is Judy Fan. I'm a cognitive scientist at UC San Diego, and I'm really excited to be here and tell you about Physion, an initiative to systematically evaluate physical scene understanding in humans and AI systems, a problem that I also think of as being quite well aligned with the theme of today's event. Also, at the very start, I wanted to acknowledge that this work was a serious team effort by everyone on this slide. I want to offer a special acknowledgement to all 4 co-first authors on their work and leadership, Dan Baer, Eli Wang, Daniel Morovka, and Felix Binder. And a very special thanks to Dan Yeamans, a major creative driver behind this work. Imagine that you're in a kitchen. Each of the objects that you push, lift, and pour behaves in ways that are characteristic of its physical properties, its mass, shape, friction, elasticity, and so on. And although you and I may take it for granted, we humans have an exquisitely well-calibrated understanding of how the physical world works, an understanding that we can leverage to achieve our various goals, including preparing an amazing pizza. And a major goal that many of us share is to develop AI systems that interact with the physical world as effectively as we do. But how would we know if an algorithm understood commonplace physics in a human-like way? And if it didn't, how could we home in on the critical missing ingredients? What we'd need is a benchmark that exposes understanding of how objects will behave over time, covers a wide range of different physical phenomena, and does so in rich and realistic environments. Now, there are already several datasets out there that probe physical understanding to some extent, but they all fall short on at least one of these key dimensions. In 2021, at NeurIPS, we introduced a new data set, which we call Physion, that meets all three criteria. The goal of my talk today is to tell you, first, what Physion is and what we learned by using it. Next, I'll show you some tools that our team developed to make it easier for you to use Physion in your own work. And finally, I'll close by sharing with you where we're headed next towards tackling some of the major outstanding challenges at the intersection of computer vision, AI, and cognitive science. Our first Physion paper made three scenarios with complex object interactions, a unified evaluation protocol to evaluate physical understanding in models and humans, and systematic comparison of state-of-the-art model and human performance. The current release of Physion consists of movie clips featuring a wide range of physical phenomena across 8 scenario types. In this work, we prioritized foundational physical concepts that had previously been studied in cognitive science. Perhaps one of the most widely used scenario types in studies of human physical prediction in 3D environments makes use of towers of precariously stacked blocks, which we call support. These support scenarios are interesting because they probe understanding of physical stability, an abstract property of scenes relying on an understanding of how gravity and other forces act on objects. And as part of Physion, we procedurally generated a large number of these scenarios using the 3D world simulator with different numbers of objects, different forces, and in a variety of different visual contexts. Collide scenarios focus on projectile motion and collisions between two objects. In contained scenarios, you have to understand how well one object can contain another. In drop, the dynamics depend on how objects fall and bounce off of each other. Then there's link, in which an object's motion is weakly or strongly constrained by attachment to other objects. Roll emphasizes the difference between rolling and sliding as a function of object shape. And dominoes measures understanding of spatial relations, momentum, and sequences of multiple collisions. And finally, drape includes cloth-like objects interacting with rigid ones under the effects of gravity. Now, with such a wide variety of scenario classes, it's not immediately obvious how to specify a task that is both well-defined across all of them and also natural for people to do, meaning the kinds of everyday physical prediction that's most relevant to human observers. If you focus on only a single physical domain, for example, block towers, then there might be an especially salient physical property, such as stability, and then you can conduct all of your evaluations using stability. But if you're looking at a ball about to roll down a ramp, being asked to judge whether the scenario is stable or not is a lot less informative about the scene. It's also worth specifying a physical prediction task that is actually natural for people to perform, that they can easily understand and are capable of performing. While pixel level next frame prediction is generic, it's not at the appropriate level of abstraction to be a viable behavioral output for humans. On the other hand, eliciting high-level event-based predictions is natural for people to both do and report on. And to meet these two conditions, we developed the Object Contact Prediction task. The OCP task asks an agent to consider two objects with a special status, the agent and patient. Then make a prediction based on the presence and kinds of other objects and forces there are in the scene as to whether the agent will make contact with the patient. What's appealing about this task is that by varying those other objects and forces, it requires agents to accurately forecast how the various objects in the scene would physically interact with each other in a generic way. At the same time, the final judgment concerns whether a specific event will occur, making it a natural way to probe human physical scene understanding. So here's what the task looked like to the human participants we recruited in order to provide a benchmark that we could use to rigorously evaluate state-of-the-art models against. The agent and patient objects were pre-cued at the beginning of each trial, but otherwise were visually indistinguishable from the other objects in the scene. After the first few frames, and well before any objects could come into contact with the agent, people were asked to predict whether the key contact event would occur or not. And for each of the 150 videos in a given scenario class, we collected predictions from 100 human participants. In parallel, we elicited predictions from 11 state-of-the-art models on exactly the same set of videos. And because these scenarios were procedurally generated in 3D World, these predictions could then directly be compared to the ground truth future states of the scene, allowing us to compute objective measures of performance for both human and machine agents. We collected these predictions in parallel for all 8 scenarios in our data set. And to be clear, this was a Herculean effort for our team. And these human experiments were led by Felix Binder. Our next challenge was to develop a unified framework for training and evaluating physical understanding across models with potentially very different architectures. We conceptualize each model as consisting of 3 modules. First, an encoder that takes in input. In the standard case, a series of RGB frames making up the video. The output of the encoder module feeds into a dynamics module that tries to predict the evolution of the state beyond the input frames. Note that the architecture of the dynamics module will vary depending on the format of the latent representation computed by the encoder. So for object-centric encoders, these were RNNs operating over graph-based representations. But for non-object-centric encoders, these were standard RNNs operating over tensor representations. While all of our key vision model baselines operated directly over video inputs, we also included a bypass for particle inputs to the dynamics modules, which are already 3D. The reason why these particle input models are important and useful, even though we're primarily interested in physical prediction from vision in this work, is because it can help us disentangle limitations due to the encoder from limitations due to the downstream modules. The final and third component was a readout module mapping the latent representation to a prediction about the scenario. Will the 2 objects touch? With this generic evaluation framework in hand, we surveyed the recent literature to obtain a diverse sample of publicly available models that each represented plausible hypotheses about how to achieve generalized physical prediction. We knew we couldn't conduct a comprehensive evaluation in this work, but we did prioritize including models that spanned a wide range of different architectures, from more generic vision-based models like SVG to architectures with stronger object-centric inductive biases, such as OP3, DPI, GNS, and RPin. We also made sure to include models that varied in how they were trained. Some were supervised with ground truth object metadata, such as RPin, and others self-supervised on pixel reconstruction, like SVG. We obtained several key results based on our parallel evaluations of models and people. So here I'm going to plot accuracy on the test set videos on the y-axis and all agents along the x-axis. I also want to be sure to mention that this work was the product of joint leadership by Eli Wang and Dan Baer, with key contributions from Damien Morovka. Our first observation was that humans are good, but not perfect at making these predictions, averaging about 75% correct. Second, none of the computer vision models we tested came close to human performance, though some were significantly better than others. In particular, models that receive supervised or unsupervised training signals related to objects, rather than simply predicting future pixels of a movie, achieved higher accuracy. This suggests that explicitly abstracting away from the pixel level might be important for physical understanding. This is consistent with another key result from our experiments. Models that take particle-based object meshes as input approach human-level performance. Of course, these models solve a much easier problem than humans do. They don't have to infer anything about physical state from visual inputs, but rather have a rich, explicit, accurate scene description given to them directly. And since our goal was to identify candidate models that could not only perform well, but also behave in a human-like way, we computed a measure of human model consistency. And this is what I'm plotting on the right-hand side of the slide. This tracks how similar the patterns of errors that were made by each model in comparison with our human sample. This analysis revealed a striking correlation between performance and human consistency. In other words, models that approached human-level performance also made more human-like predictions. However, while some of the particle input models achieved human-level accuracy, there remains a significant gap to close to achieve human-like physical prediction. Taken together, these results suggest that a model's latent scene representation is critical to its prediction ability. We think then that a crucial open problem in physical understanding is building models that learn to abstract out an explicit physical scene representation from pixel inputs. I've so far told you about what problem the Physion dataset and benchmark was designed to solve, and some initial insights we gained from conducting some evaluations of models and benchmarking them against human behavior. But I'm here to tell you that the evaluations we've done so far are just scratching the surface. Our real hope for Physion is that it will be a useful resource to the broader computer vision and AI community to help you and your colleagues benchmark your own or others' models and understand how well they're approximating human physical prediction. Here are some pointers to publicly accessible resources we created to help remind you of key details about Physion and our main findings, our GitHub repo where you can easily download the full dataset, including all videos and ground truth metadata about each 3D scenario, and our repo containing the code we use to evaluate the models in our paper, and some tools to help you evaluate new models more easily. I really do encourage you to visit our project website, physionbenchmark.github.io, where you can find a blog post style summary of our NURBS paper, as well as pointers to the code, paper, and dataset. We've also thoroughly documented the GitHub repo for this project. Our first release is hosted here in Physics Benchmarking NURBS 2021 within the Cog Tools Lab organization. These resources were initially developed by Eli Wang as part of his PhD, and they are currently being maintained by Rahul Venkatesh, a new member of the Physion team. So where do we go from here? First, there is a major open question raised by Physion that's of fundamental importance for understanding human cognition. What is the role of forward simulation in explaining human physical prediction? While there has been a lot of support for the simulation hypothesis over the years, in other words, running a genuine internal model of the physical world to imagine future states, that hypothesis has also been hotly contested with some arguing that approximate heuristics play a much larger role for explaining everyday intuitive physical judgments. As part of our Physion evaluations, we took a stab at this question by asking how much better models did when they generated their predictions based on the output of the internal simulation process modeled by the dynamics module than when they were only making their predictions based on the initial observed frames without simulation. So, for example, for SVG, this is the difference between the circle and the square. And we don't see an advantage for using the outputs of these internal rollouts. And by no means was SVG the exception. We didn't see a simulation-based advantage for any of the other vision models we tested either. But critically, we do see a boost when these models are shown the full movies, indicating that these models are able to exploit features of the input to detect object contact events, even if they don't support strong prediction. These results raise the possibility that the main way these vision models were able to achieve above chance prediction was by using visual features already available from the initial frames of the video, like object position, shape, and contact relationships that help to give away what the final outcome would be. And to some extent, these kinds of shortcuts might be unavoidable for the types of rigid body scenarios we tested, however diverse they were. So motivated by those findings, our next step was to begin working on Physion 2.0, which at a minimum will contain scenarios featuring variation in latent physical properties that cannot be directly inferred from a single frame, but only by tracking how objects interact and move over time, including variation in a much broader array of non-rigid materials, including bouncy materials in this example. So here's some more early demos from Physion 2.0, which will include greater variation in mass, friction, viscosity, bounciness, deformability, and more. This work is being led by Fish Tang, currently a postdoc on our team. Physion 2.0 will also generalize beyond the OCP task to include large-scale human psychophysical measurements of other important aspects of human physical scene understanding, including uncertainty, providing an even richer target for models to capture. And the final idea I'd like to leave you all with is that you can think of Physion as just one instantiation of a larger enterprise that my collaborators and I call Cognitive AI Benchmarking, or CAB for short. CAB is not business as usual in AI or cognitive science, but rather brings together the study of human cognition, the design of new algorithms, and engineering of realistic virtual environments. And this is the kind of multidisciplinary teamwork we think will really pay off in the long run. In short, CAB aims to conduct rigorous measurements of natural human behaviors, including exploration, communication, collaboration, in realistic environments, in order to reveal the size and shape of AI human gaps, and thus opportunities for next generation AI systems to fill. Thank you so much for listening. And thank you to the generous support of our sponsors, without which this work wouldn't have been possible. Please feel free to reach out to me or any other member of the Physion team if you have any questions or feedback on this work or ideas about where to take these ideas in the future. Thanks again.
Okay, so now we are taking a 15-minute short break, and we'll be back at 11.
Okay, welcome back. Here is the ECCV 2022 VOLI workshop, and we will start with Thomas Kipf's talk. So let me first introduce our speaker, Thomas Kipf. He is a senior research scientist at Google Brain. He obtained his PhD at the University of Amsterdam, working with Max Welling. For his PhD thesis on deep learning with graph structured representations, he received the Alice PhD Award 2021. He is broadly interested in developing and studying machine learning models that can reason about the rich structure of both the physical and the digital world and their combinatorial complexities. Let's enjoy Thomas' talk.
Thanks so much for the introduction, and also thanks so much for inviting me to speak here today. It's a really exciting program at this workshop. Yeah, so today I'm going to talk about a line of work I've been really excited about for the last almost 3 years now, which is essentially this line of work on slot attention. It's a new kind of architecture where we've tried enabling really easy and fast object discovery in both images and videos, and more recently also 3D. And this is joint work with many colleagues at the Brain team at Google, but also external collaborators that I'm going to present today. And so I don't think I have to kind of motivate object-centric learning all too much for this workshop, because this is kind of the theme of the workshop today. But just to give like my kind of understanding of what we're talking about. So in my view, the goal here is really to perceive and model the world using composable abstractions. And these should ideally be directly learned from like raw data in a context or task-dependent manner. And this shouldn't use like detailed kind of fine-grained supervision, but should really be something more like an emergent property. And if you look at the world around us, like the typical everyday scenes we see, they're highly structured. Of course, we have like structured data per se that is already processed in a structured form, but I'm really talking about like perceptual data. Like we perceive the world effectively just like, I don't know, in a camera as an array of pixels, but ultimately the way we understand it is in terms of objects and their relations. And if you look at these scenes, you can vividly imagine of like what's going to happen next, even though you might have never seen this particular arrangement of objects before. And so we have this kind of really strong kind of compositional way of understanding the world. And so why do we want to do object-centric learning in machines? And the reason is there's a number of reasons. So humans seem to be doing something very similar. Also, there's probably some labeled data efficiency to be gained. Right now, if we want to train kind of object detectors, we have to have like huge labeled data sets, but ultimately we can potentially get much more labeled data efficiency if we extract objects in using some kind of first principles, and also use objects as the core representation for downstream tasks like robotics or question answering. And this all comes down to compositional generalization, because ultimately, if we want to kind of answer questions about the real world, we have to really understand the components of like the objects and the entities that we want to reason about. And so the kinds of models we want to build, they should ideally not be explicitly supervised. This is just not like a very scalable way of understanding every single detail in the world. And they should ideally also work in the absence of language prompts. Like we've seen a lot of exciting work on getting compositionality in vision via language. But there's more to kind of perception than the combination with language prompting. And there's a lot of natural phenomena that we can understand in kind of a very abstract, intuitive way, just from perception only. And ultimately, we would like to learn context of task-dependent abstractions. Like there's no single kind of abstraction that works well for any task, but objects are really something that is context or task-dependent. And the way current kind of detectors are trained, they're very much like we have like one ground truth, and we try to optimize for that one ground truth. But ultimately, what we would like to have is like more context or task dependent abstraction learning. And so the kinds of architectures that have really developed in this community in the last couple of years are what I would call slot-based neural networks to address this problem. And Klaus Greff, who's going to speak later today as well, he had a great review article on this, on the binding problem in artificial neural networks. So I recommend reading that if you want to get like a bit of a background on these methods. And so they typically proceed by processing some kind of low-level perceptual input using, for example, a CNN or a transformer to get a grid-based representation. But then the core component is really to map from that grid-based representation to some higher level abstract representation, to group or abstract these representations into a set of latent variables that we call slots. And these latent variables, these slots, they can really capture any kind of object or entity in the input, or any other kind of useful abstraction that is can be understood as a component of the input. And so ultimately, this allows us to use powerful reasoning or dynamics modeling architectures like transformers or graph neural networks, because we already have like the ideal components over which to reason. And so we get a lot of kind of learning efficiency from reasoning over the right abstractions. And all of this can be trained directly using some kind of downstream task or loss. And so the core component here is really that everything that happens in this kind of slot space or latent space is symmetric under permutation. So there's no real meaning for slot 1 to be slot 1. The slot 1 isn't like specializing to be like a car or a dog slot, but any slot can capture anything in the input. And so this has motivated us, like this high-level motivation has motivated us to work on try to come up with like a really efficient architecture to address this problem. How do we move from like low-level perceptual input to some high-level structured abstractions? And what we came up with was this architecture called slot attention. And it's really just a very simple kind of iterated cross-attention mechanism that has like a competitive aspect to it. And that competitive aspect, that leads kind of towards the kind of emergence of objects, because one single, or that facilitates the emergence of objects, because one single slot can only explain one particular part of the input. And if that part of the input is already explained, another slot cannot explain that anymore. So it has to pick something else. And that simple kind of competition mechanism over multiple iterations when trained for some kind of downstream tasks seems to be leading to the emergence of objects in these kinds of cases. And so we can train this module, and we can put it in an autoencoder and train it for unsupervised object discovery, but we can also put it in like an end-to-end detection architecture and use it as kind of a set prediction component, which is like one of the predominant mechanisms of doing detection vision these days with methods like detection transformers. And so the core prediction problem we're looking at really is to learn a mapping from an image or some other modality to a set of variables. And so intuitively, each set element should capture, say, an object, a part, or say a part of the background in each of these slots. And so this is quite similar to capsule nets, if you remember them from a couple of years ago. But here, the slots are really symmetric, are exchangeable. So in capsule nets, every kind of capsule, and you also do routing to learn these capsules. They have a particular meaning, like they're a particular category, like one capsule for a dog or one capsule for a house. And then you need to come up with other mechanisms to break the symmetry, like you have convolutional capsules, for example. But it turns out if you just remove the specialization from this representation and you just make everything exchangeable or symmetric, then you get a lot of these emergent behaviors for free, and it's also easy to implement. And so in terms of implementation, the module is really relatively simple. We start by taking the inputs. These are, say, feature maps processed by a CNN or some kind of backbone. And then we just apply some position embedding on top of those. And then to get the initial slots that we want to now populate with the input features, we can initialize them just at random from a normal distribution, or we can also learn a particular initialization for them. And so over a number of iterations, what slot attention effectively is doing is we compute dot products of like a key query attention mechanism where the keys and the queries are learnable transforms of the inputs and the old slots. And then just like in regular cross attention, we compute a softmax over these scores divided by some temperature. And the core difference to regular cross attention here is that we normalize the softmax over the output axis, over the slot axis or the query axis, whereas usually in cross attention, you would always normalize over the key or the input axis. And the reason why you would normally do that is so that everything is nicely normalized and everything sums to one. But here we really want to have competition so that one slot can only explain one particular thing in the input, and then another slot cannot grab the same thing ideally. And now, because we normalize it over the output, we need to renormalize over the input or do a weighted mean instead of a weighted sum to get like a stable update. Or we can use layer normalization as some other trick to normalize things post hoc. And so the final step is then to write these updates that we computed into the slots, and we can put like a learnable function there, like gated recurrent unit works quite well in practice. And we also use things like layer norm, just like in regular cross attention. Now, what we only realized after we came up with this method and implemented it, we realized, okay, this is actually quite similar to like just a regular k-means clustering algorithm. And if you write down a soft version of k-means, it looks as follows: like you initialize your slots or your cluster centers, and then also for a number of iterations, you compute some scores. This time you get them from the squared Euclidean distance, and you compute a softmax also over the output axis, and you compute a weighted mean to get the updates. And finally, you write the updates directly into the slots. Now, the core difference here is that there are no learnable components in here, and the slots are also the updates are directly written into the slots. And so what soft k-means does, it kind of implicitly minimizes like the squared Euclidean distance and uses that as like an objective function to cluster the kind of input. And on contrary to that, in slot attention, we have learnable components in there. And so what the clustering that effectively happens is driven by whatever downstream task we have or whatever kind of downstream loss we optimize. And what we can also see with this connection to clustering or soft k-means is that slots have to compete for explaining parts of the inputs because they behave a bit like clusters. And so we can now put this architecture, this module into a simple autoencoder where we take an image, we encode it using a CNN or some kind of backbone. We use a slot attention module with a couple of clustering iterations, and then decode back into the image space. And so we use a decoder, a spatial broadcast decoder that's applied independently per slot, like in this iodine paper mentioned here. And we decode not just RGB values per slot, but also an alpha channel or logits for an alpha channel. And these are then used to recombine everything into a single image. And the only loss we use for training is an L2 loss in pixel space. And so when we train this model unsupervised on say this clever data set here, then what we find if you visualize these individual kind of slot reconstructions is that so we can visualize them basically by the RGB and alpha mask. So we get the alpha channel here is just shown as white if it's one, and so we get these semi-transparent kind of reconstructions for each of those slots. And so what you can see is that the individual objects are really decomposed and captured by each individual slot. And the model also does something like amodal completion. And this is similar to prior work on object-centric learning, but here just with a pure attention mechanism. And for example, what would happen if we take slot 11 in the first row here and delete it from the representation, then slot 5 would kind of be rendered in its completeness, like it would render the entire sphere, even though in the input, it's never seen the entire sphere in this particular example. So it has like an internal representation of the entire input. Now, this was kind of exciting for us. Like we started mostly on images, these kind of simple image data sets, but it turned out it was actually really hard to scale this to more complex data. And so one aspect we were interested in is kind of, if you look at like the world around you, like a lot of the things that drive object perception is motion cues in the environments. And of course, if you want to learn from motion cues, like the most natural thing to look at are videos instead of images. And so in this line of work, or in this work on object-centric learning from video, essentially our motivation was like the world is not static. And at the same time, temporal dynamics tell us a lot about object structure. So if you have any kind of movement in an image or in a video, then this will likely be a strong cue for this being a useful abstraction or useful representation if a single component moves and the rest is static. But also the other way around, if you want to model dynamics in videos, if you want to predict the future, then it can be really useful to already have like a structured abstraction, because then it becomes a very simple physics modeling problem. And lastly, if you have these these temporally consistent abstractions, they can also serve as a useful basis for many downstream tasks like VQA or learning some kind of policies on top of those representations. And so we essentially just developed a relatively simple extension of slot attention for video that we call slot attention for video, or short SAVI. And the main difference here is really that we use the slots that are discovered at one time step for one image as initialization for the next time step. So instead of randomly initializing or using a fresh initialization for the cluster centers or slots at every time step in the video, we just start from what we already know from the last time step. And we typically also put a small learnable module in between, like a self-attention transformer. And so what do you get when you apply this on this simple robotics data set here? Then you can see that the model still reconstructs these videos faithfully, but it also decomposes them and discovers the kind of interesting components in those environments. So it gets all the objects, and it also like decomposes a gripper into its two gripper pieces or gripper arm pieces in that move independently. And one interesting aspect, if you think of this like, okay, you start with the slots, you abstract them from one scene, from one image, and then you use them as a visualization for the next time step. You can also ask the more general question of like, what happens if we initialize these slots with some other kind of context information? Like, let's say we have some kind of context that tells us of how we would like to perceive the scene, or what information we would like to put into each slot. So we can also, to test this, we can essentially initialize those slots using some simple object cues. Like we can give the model access to segmentation masks or bounding boxes, or just the center of mass coordinate of an object. And we feed that through a small kind of learnable component like an MLP, and use that to initialize these slots. And then what we can see is that we effectively get like a controllable decomposition of these scenes. Like we can always say, okay, the background should always end up in the first slot, and then each of these objects should end up in a particular slot. And that, especially if scenes are more ambiguous, where it's not entirely clear how a scene should be decomposed, this can be used to break some of these ambiguities. And so we can effectively get controllable video decomposition by conditioning on some initial information in the first frame. And so we took this one step further and applied this method on some more complicated video data sets, where we rendered scenes with textured backgrounds, like real world backgrounds, and also 3D scanned objects in those videos. And then we trained a model like from scratch on a data set of these videos generated from a library called Kubrick. And effectively what happens is that the model, first of all, learns to decompose these objects but here in this case we use optical flow as an additional signal to help the model find the right object decomposition. Because what we find typically is if you have textured scenes and you just use L2 reconstruction in pixel space, the model typically tends to struggle to find the right decomposition. But using optical flow as a reconstruction target is one of the ways one can avoid that issue. And so by initializing the slots using, for example, bounding boxes in this model, we can now steer the decomposition that the model finds of a scene at test type. For example, we can condition a model on a bounding box of like this group of objects, like these two fists, and then the model learns to attend to and track those two objects together in one single slot. And this is also the kind of signal it saw at training time. It always only saw one conditioning signal for both of these hands. But at test time, we can also then just see what happens if we condition the slots or initialize the slots so that they should attend to each of those parts independently. And so the model So if we do this, if we provide bounding boxes for those parts, the model can also independently decompose them and independently track them. And so this is a nice way of breaking kind of this ambiguity in scene decomposition in a non-hierarchical way. So we don't have to define an explicit hierarchy, but we can essentially address the different levels of the hierarchy just via context signals, like via these conditioning signals that we give to the model. And now I've already shown you that we were able to scale these models to some more complex texture data sets, and I mentioned optical flow as one target. But we recently tried to scale this further to like real world driving data. And so one of these issues of these unsupervised object-centric learning methods in the past couple of years was essentially that any kind of attempt to really scale them to rich and textured scenes typically led to some unfavorable decomposition of those scenes into, say, spatial regions. What we found is that with just a few like scaling tricks and using LiDAR and depth as a training signal, we can train these models on data sets as complex as way more open and get some interesting object decompositions and tracking. And so the model here is relatively straightforward. It's effectively we scale like this earlier version of SAVI by using data augmentation, like we just crop and rescale all the video frames we have, like just a standard procedure for computer vision techniques. And we also use a more scalable hybrid attention convolutional encoder. And other than that, it's basically just slot attention applied on top of those feature maps. And we hook up the slots over time using a simple self-attention transformer. So the slots discovered at time step 1 are passed through an self-attention transformer or transformer encoder, and then acts initialization for the second time step. And the only loss we really apply is a reconstruction loss in pixel space, where we task the model to predict the depth that we measure using the LiDAR. So the ground truth is like the sparse depth signal, and we only apply the loss in all the points where we have a measured depth signal and ignore all the other points. And using that simple kind of setup, we get emergent segmentation and tracking in these data sets. And of course, we can also use like conditioning here, for example, using bounding boxes to break some of these ambiguities and to tell the model which exact objects to track. And so this is what the data looks like. So we have these driving scenes, and the LiDAR is really pretty sparse, but we can only effectively apply the loss in all the points that we measure. And at test time, we just feed the raw camera input. So at test time, we don't need LiDAR anymore. This is really only used for the training signal. And as I mentioned before, the only loss that is applied here in the entire method is just an L2 loss in pixel space on this LiDAR signal. And now if we run this model on the Waymo open data set, and these are our test scenes here, then this is roughly what we get if we train the model in a conditional setup. And so conditional here really means that we use bounding boxes as initialization for those slots, and then the model learns to bind this bounding box information to the respective car in the input and approximately track it and segment it over time. Now, these results are far from perfect, but you can see that there's quite some interesting emergent tracking happening, even though some of those slots, especially when an object disappears from the scene, they start to grab a new object, or they start to grab some environmental parts of some parts of the environment. We can also run the model in a fully unconditional setting. That means we don't provide any kind of bounding box cues, but we really just run the model using random or learned initializations. And then the model also learns to capture the cars into slots, but there's a lot more noise in the results. Like we also have like environmental objects being captured in slots, or slots switching a bit more readily between objects. But I think it's a very interesting first result for scaling these methods to more complex video data. So before I wrap up, I would like to go one step deeper into what can we like to look into the question of what can we do with those slots that we learn from video data and use them for downstream tasks. Like, are these actually useful for say visual question answering or controlled downstream tasks? And this was a collaboration with Animesh Garg and C. Wood and Nikita Dvornik at the University of Toronto. The method we call slot former. It's a method for unsupervised visual dynamic simulation of object-centric models. And so the core of this method is really we use SAVI, like slot attention for video on video sequences to extract temporally consistent slots. And then we use a transformer module to basically a big transformer to predict the next time step evolution of those slots. This simple recipe allows us to learn consistent long-term physical dynamics solely from visual input and address tasks like this fire task here that I'm going to go into a bit more detail. And so slot former really is in its essence is a SAVI encoder that we pre-train. So we take those scenes like at the bottom here, we run it through our SAVI model and get abstracted slot variables from the visual inputs. And this is pre-trained. So we first train SAVI in an initial stage, and then in the second stage, we freeze the SAVI encoder and only get the slots. And then in the second stage, we use the discovered slots over time to predict the slots at the next time step effectively. And we make a few changes to the standard transformer prediction setup. We only use temporal position encoding, so we don't encode the slot position because we don't want to break the symmetry. And we also, in addition to predicting the next latent slots and putting a loss, an L2 loss on the next time step prediction for the slots, we also predict the visual output. Like we use a pre-trained SAVI decoder to predict what the video would look like at that time step, and we also apply visual loss. And then we can just feed those slots back in and auto-regressively iterate with, for example, a number of burn-in frames, or just starting from a single frame. And so this simple recipe allows us to effectively do consistent compositional video prediction from just a single frame. So we train this here on this FIRE data set, which is a compositional physics modeling data set, where you also have to, in the final task, place an object in the scene, and then the green object has to hit the blue target object. And so we can use the dynamic simulation that we learn to then inform the policy of kind of where to place objects and see if we can get some efficiency improvements out of that. And we can also use it for visual question answering by effectively like answering video questions. For example, will the green object and the purple object collide in this simple cleverer example here? And the past state-of-the-art model for this effectively took the input video, abstracted into objects, and then used a big transformer to run question answering on this scene. That's one recipe that a previous Soatto model used. And so what we do instead is we take slot former, which is pre-trained unsupervised, run it on the past frame to get the future rollout of what the video would look like in the future. And then we use a supervised question answering model to answer those questions. And that gives us a relatively strong improvement on those predictive VQA tasks on Cleverer. And it also allows us to get really strong performance on this Physion benchmark that you've seen in the past talk this morning, and also in FIRE for action-based, for vision-based planning, where we get strong results without any additional kind of mask or object bounding box supervision. And so just some visual results of what this looks like. So you can see on the left-hand side always a ground truth, and on the right-hand side the slot former predictions. And the model does a pretty decent job at getting the compositional dynamics, even though these are really compositionally complex test scenes that the model has never seen before. And lastly, these are some results from Cleverer, where some of those baselines produce either visually pretty coherent results, but then objects switch kind of identity over time, or they start to blur out over time or have inconsistent dynamics. Whereas in slot former, we get really like a pretty faithful representation of the ground truth evolution of the system. And so with that, I'd like to conclude, and I hope that in this talk, I've shown you some exciting results, especially with SAVI++, that self-supervised object-centric learning is no longer constrained to simplistic toy environments, and that we can really start using some of those benefits for some real world results. Of course, these are still in their infancy, but I think this is going to be an exciting area for future research. And at scale, these methods are likely going to be useful for things like interactive scene editing in 3D, and there we're going to have Klaus's talk in just a bit. And for things like causal and physical modeling, visual reasoning, and robotic manipulation. And especially like the data efficiency gains we get from something like slot former make us really kind of excited about how like this can be useful for many of these downstream tasks. And so with that, I'd like to thank all my collaborators at Google Research and also the collaborators at University of Toronto for the slot former work. And I think we have some time for questions. Thank you.
Okay, thank you so much for the talk. Yeah, I'm seeing one question from the audience. So is it possible to also model the relationship among the slots? For example, the objects in the scene may have spatial relationship or other semantic relations.
Yeah, that's a great question. So effectively, the question is, where would this information come from? Right now, this would be somewhat implicit in the model. So let's say we have scenes like here, or let's maybe look at this kind of scene here where we have the discovered object slots of the model. And effectively, once you have this kind of abstraction, and let's say this abstraction also encodes like where an object is in space, then the transformer by itself could figure out like these spatial relations. But that being said, if one, for example, has additional information that describe the spatial relationships, for example, like information on the kind of pairwise relation between two objects, one could put that in as additional side information into the transformer, or one could also use architectures like graph neural networks that have an explicit mechanism for handling pairwise relations. So I think there are interesting ways of including that information. At the moment here, we didn't find that this is actually necessary. Like, you can do a fairly good job on these tasks by basically just using those abstractions that the model finds. But yeah, thank you for the question.
Yeah, thanks. And I'm seeing another question. Is the number of slots determined based on the task? Will different number of slots influence the performance?
That's a very good question. And so for the slot former work, most experiments here used something like 6 to 8 slots. And there is some difference, like depending on how many slots you choose, you get different performance. And there is some robustness, like it doesn't need to be exactly the perfect like ground truth amount. Even the ground truth amount sometimes is not like the ideal because there's some noise. But effectively, we typically either, if we know like how many objects there are at maximum in scenes, and we typically choose that number plus maybe some buffer. Here in those scenes, I think for slot former for fire, we used 8 slots, which is even though there's kind of 3 main objects and then a pretty wide variety of like environmental objects. Like here, you have many of these environmental objects. But then if you don't choose enough object slots, and what the model effectively does, it, for example, here in this case, it groups many of these environmental objects here into just a single slot. So the model, if it doesn't have enough slots, it has to kind of make use of whatever capacity it has to group the things it has in the environment. If you give it too many slots, then there's a number of failure modes that can happen. Like, for example, two slots or multiple slots can try to compete for the same thing and end up in some weird segmentation of an object. They can also properly capture the parts in an ideal world, even though I'm not really sure if that happens in practice. But there's a lot of kind of failure modes that can potentially occur. So yeah, there's still some tuning needed to get the right number of slots.
Yeah, so if I can follow up a bit on that. So if we have extra slots, so do you see more frequently that the extra slot is breaking the background into oversegmented background in a union, or it tends to oversegment the objects? Like you said, break that into parts.
That's a really great question. I think it really heavily depends on the data set. Like in this example here, the model had was trained on scenes with 6 objects, but with 11 slots in the top 2 rows. And so here it just learns to keep things, keep slots empty in this particular case. But this is not always the case, especially if you have complicated backgrounds. Then indeed what typically often happens is that it uses quite a bit of capacity on the background and chunks the background up in various ways. A typical failure mode is also that one object like is competed for by multiple slots, and especially for many slots, then this competition mechanism, if you run slot engine for 3 iterations, might not be done yet, and you have like a semi split up object that is not fully decomposed or not properly captured by a single slot.
Yeah, and one last question. So for the slot former work, are you training one model for all different type of dynamics? How well does the model generalize to novel unseen dynamics?
That's a really great question. So what we do here is we have these 3 data sets, effectively 3 tasks, like Cleverer, which are these scenes here, Fire, which looks like this, and Physion, which I'm not showing here, but there was a talk just earlier today. And for each of those data sets, we train a separate model. But within Fire, for example, or within Physion, there's quite a few different kind of, I think Physion is an interesting example because Physion has like 8 different prediction tasks or 8 different settings. And we use a single model for all of them. So we use a single big transformer that can handle all of them. It's doing well on some and not so well on others. I think like the cloth task where a cloth falls down and you have to predict whether it touches a certain object. I don't quite remember if that was really, really difficult for the model, or if that was actually easier. But there were quite some outliers depending on the task. So some dynamics seem to be more easy to model in those environments.
Yeah, thank you so much, Thomas. It's great to have you.
Yeah, thanks so much.
Yeah, maybe Jiayuan, you want to proceed with introducing the next speaker?
Yeah. Next will be Klaus Kipf. And Klaus Kipf is a research scientist at Google Brain in Berlin and a PhD student, previously a PhD student like at IDSIA with Jorger Smith-Huber. His research focuses on the binding problem in neural networks, on learning object representations, and in particular, on unsupervised object perception. His work received an outstanding paper award from IEEE Transactions on Neural Networks and Learning Systems. And next, let's enjoy the talk from Klaus.
Thank you. Thank you. Can you guys hear me all right? I'm sorry, I didn't get a chance to
we can hear you. You can share the screen so we can help you check. Yeah.
Perfect.
Yeah, we can see the screen. Yeah. Excuse me, you are muted. You're muted. Yeah. Hi, Klaus, you are muted. Yeah.
Now it's better, right? Can you
Yeah.
hear me again?
Yes. Yeah, we can hear you. Yeah.
All right. Sorry for the hiccup. Thanks for the introduction and thanks for the invitation. Pleasure to be speaking here. As was already mentioned, my research interest is mostly on object representation learning, and I spent a fair amount of time thinking about how is it that we can go from an unstructured input, such as pixels in an image, to object representations. How does the how does the brain take care of that? How can we map that into neural networks and do so in a mostly unsupervised fashion? I think this is one of the core unsolved problems. But as Thomas has already talked in quite length about today, we have made some progress. And because this workshop is focused on objects and interactions, which I sadly have not worked on much, but I thought I'll talk about something different than today, namely how 3D structure factors into this. I've recently become interested in combining object perception and 3D structure to get a 3D understanding of the world, of the scene, of the inputs. And this is an extremely fascinating area, and I think it is complementary to object perception, and it is also crucial for interaction. Before going any further into this, I want to briefly point out that when I mean inferring 3D structure, I'm not just talking about like the 2.5D depth perception, depth estimation that is sometimes done. But instead, I want to point out that when you looked at this image, you inferred the backsides of the objects and made some guesses about what the whole objects looked like. You did some amodal completion, as it's called in cognitive psychology, and some filling in. So there is some under the hood reasoning happening about the hidden parts of the scene as well. So why is 3D structure so important? So if we want to interact with the real world and not just via images and our computer screens, for example, in robotics or the like, we need to navigate the real world, and the real world is 3D. So having a 3D understanding of the surroundings is crucial. It's also crucial if you want to manipulate objects, if you want to grab, interact, or grasp objects. For these tasks, just knowing which region in the image corresponds to the object is not that helpful. We need to know where in 3D space is the object, which parts of the object are stable and grippable, what's the shape of the object, what are the affordances. The 3D structure of the scene is also critical for physical reasoning. Physics is pretty convinced that our world is mostly 3D, maybe 4D if we count time. At least a 3D model of the world is an excellent abstraction to do physical reasoning. And physical reasoning is very important if we want to make predictions in the real world. The 3D structure of objects is also critical for recognizing objects if they are in different circumstances. They have a different pose, they are in different lighting conditions, they are partially occluded. And since it is very important to be able to generalize across the shape dimension of objects, having a thorough 3D understanding of the scene is important there too. And last but not least, it's also important to be able to communicate with others. Okay, if 3D is so important, we would expect our brains to spend quite some effort on it, and that is actually also the case. There's quite a bit of work in cognitive psychology showing that there's numerous cues that our brain evaluates, pays attention to solve this under constraint problem of mapping a flat 2D image onto a 3D representation of the scene. There's obvious things like looking at light and shading, occlusion, things that occlude each other or can give some information about what's in front. There's shadows. There's more subtle things like texture gradients. So the way a texture gets finer and finer into the distance tells you something about the slope of a surface. There's visual effects like haze that comes into effect for long distances. And there's depth of field for, like, our eyes have only a narrow focus. And that can tell us something about the 3D nature of the scene as well. Of course, this doesn't always work out, and there's some fun illusions that demonstrate in which ways our depth perception and 3D understanding can sometimes go wrong, like the Amos room illusion, or the forced perspective photography that people often like to do. But in general, our brain does a surprisingly good job and uses all kinds of cues to have an extremely stable 3D perception of the world. And that is also very critical for our everyday life. All right, so if 3D is so important and we want to make use of it in our neural networks, how should we go about representing a 3D scene? If we look to computer graphics, 3D software, games, movies, special effects, scenes are usually, like objects, are usually represented as meshes, vertices and faces with some associated materials, and then a ray tracer simulates the way light scatters and renders that into an image. For the purpose of neural networks, however, this representation is quite cumbersome. Varying numbers of discrete entities like faces and vertices make it very hard to make the system differentiable. And even though there is definitely some work that tries to learn meshes, even differentiate renderers into meshes, it is a tricky business. Also with things like topology, having holes in a torus, for example, is a complication there. Another straightforward way would be to use the 3D equivalent of pixels, namely voxels, and just cut 3D space up into a grid of small cubes. And then, similar to having feature maps in a convolutional network, we could just populate each one of those blocks with features for that part of the scene. However, this is either extremely coarse, like in this example, or extremely memory hungry, because if we want to tile 3D space with 1,000 by 1,000 by 1,000 voxels, that quickly grows so ridiculously large that we run out of memory. One way around this that has recently become quite popular is representing a 3D scene as a neural radiance field. The idea there is essentially to, instead of having a discrete grid voxel representation of the scene, we instead represent the scene as a neural network, as a function that maps the XYZ coordinates of that space onto a density and a color. So in effect, instead of having a huge array where all the features are, we have a neural network that implicitly handles all of that and can directly spit out for every position in space the corresponding density, how opaque it is, and color. One remaining problem with that, though, is that it is very compute hungry. Essentially, the reason for that is that what happens to render an image with a neural radiance field is that for every pixel, you compute a ray through the volume of the scene. And along that ray, you sample hundreds of points. Each one has an XYZ coordinate, and for each one of those points, you pass it through the neural network, typically a small multi-layer perceptron, to then get a density and a color, which is then integrated along that ray to figure out that this ray first hits the yellow, so the yellow does occlude, and the purple that comes later is not being visible. Which means that to render a single image, we have, for every pixel, we have to run this small MLP hundreds of times. And yes, GPUs and graphic cards are very fast these days, and it can be done, but it is still a matter of seconds or minutes for a single high resolution image, and for training, this can be quite slow. There's lots of tricks, and these things are being improved every month, but in general, this is a pretty slow approach. What I want to advocate for today is a slight variation on this. It's taking a step back again from 3D a little bit by taking a light field parameterization. So the idea is, instead of querying a network for every point along that ray, we just train a neural network to, given the ray, so essentially just for one pixel, we construct a ray. We know where the camera is in 3D space. So we know the origin of that ray, and we know the direction for that particular pixel. We just feed that the representation of that ray into a neural network and train the neural network to directly give us the color. So this, in effect, saves us a few hundred times running the neural network, because we only have to run it once. But the neural network now has to implicitly understand the 3D structure of the scene. It has to internally resolve any occlusions that might happen, and so on. The upside, of course, is that it is much, much faster, and it is much easier to deal with later. Okay. Another problem with neural radiance fields for representing a scene, though, is that what typically happens is that you have a whole bunch of input images on the order of a few hundred usually, sometimes only a few dozen. If you regularize well, even less can do. But then you optimize this neural network for that particular scene. So afterwards, you have a neural network that, in its weights, has internalized the entire structure of the scene, which allows for some impressive and fantastic novel view renderings that are quite high quality and surprisingly nice. But there's no transfer to novel scenes. If we have a novel scene, we have to again optimize a neural network, and the representation is also not. It's not obvious how to use that representation because it's all implicit in the weights of that neural network. So instead, what I want to present to you today is the scene representation transformer that came out of our group, which addresses which combines light field parameterization, as I mentioned before, with an amortization process. So instead of training a neural network for every scene anew, we now train an encoder. The idea essentially is that we use novel view synthesis as a training objective, meaning that for every scene, we have a handful of images, not hundreds now, just 3 to 5 maybe. We pass these into an encoder. And the hope is that the encoder can transform these into a representation for that scene that we can then use to render novel views, and that we can then later use to understand that scene, to interact with that scene, to deal with these things. And so what we do is after we have this latent representation, in this case, because our encoder is a transformer, it's a set of tokens, a few thousand tokens that then give a representation of that scene. We then have a small transformer decoder. This is only 3 small transformer layers. And as I said, in the light field parameterization, what we do is for every pixel of our desired target image, we construct an array that we embed, make it a query for our transformer, which then attends into the scene representation and then outputs for that pixel the corresponding color. And then once we have for the camera pose of the target view that we want to have reconstructed, once we have the reconstruction, we can then just compute the mean squared error with the actual ground truth target view and backpropagate that through the entire system and train the system. So this is novel view synthesis as a training objective, essentially amortizing the optimization that the nerf is doing. And then what we did here is we just trained this in a completely unsupervised fashion, apart from the given camera poses that we had for all the cameras, on a data set we generated of scenes like this, with 16 to 32 random ShapeNet objects tossed in the middle, in front of 500 or so backgrounds. And then the interesting thing that comes out of this is that despite the fact that there is no strong inductive bias to make this a 3D representation, we find that the reconstructions of the model are still very much 3D consistent. So if we generate novel camera views, as shown here, you can see that it really looks like the camera is actually rotating around the scene. It does not work well if we move far outside of the range of cameras that were seen during training. So if we zoom too far in or too far out, things will break down. But in a reasonable range of camera distributions, this actually looks very nice. And we've actually also not just applied this to generated toy data sets, but also to Street View data, where again, we have some 5 input images that look something like this, and can then generate interpolations, camera paths that demonstrate that the model has captured some of the 3D structure of these actual real-world scenes. Surprisingly, it is even able to capture a little bit of things like reflections implicitly, and even in this example to the left, the movement of the car, although obviously the movement of the car here is entangled with the perspective. So time and space are completely entangled in this regard. So as you turn the camera, the car will move. We've also trained, like after training in an unsupervised fashion on just novel view synthesis, we've also then trained a separate decoder, frozen the encoder, keep the scene representation the same, but train a separate decoder for semantic segmentation. For Street View, we had access to a few core semantic segmentation maps, and therefore train a separate decoder. This was meant to show that the representation really is useful, that comes out of this. And as you can see, even for novel views, it produces a reasonable semantic segmentation. Just as a small thing, I've mentioned that we need camera poses, but that's not entirely correct. We need camera poses for training, but we can actually get away from camera poses at test time, because we can simply not feed the camera pose into the encoder. And to generate the target view, we can use a relative pose to one of the input views. And it doesn't deteriorate training much at all. Then we only need poses during training, and during inference time, we can actually just feed 5 unposed images and produce novel poses to show around the scene. Okay, so far I've talked a lot about 3D scene representations, but where are the objects? This is the next thing. To integrate objects into this, we tried the simplest thing that we could think of, which was to just take slot attention that Thomas has explained in detail before. And instead of using the set latent scene representation, the tokens that we generated before, we now first run a slot attention on those tokens and generate a few slots, basically clustering that scene representation into a few slots. And then we have a slightly different decoder that now looks into these slots to generate the output view. The slot mixer architecture, I'm not sure I want to go into too much detail, but just very briefly, the idea is that where the normal scene representation transformer decoder was just a transformer decoder cross-attending into the representation, we now have a bit of cross-attention going on, but in the end, we only keep the final weights, final attention weights into these slots, basically for every pixel deciding which slot this pixel belongs to most. And then we use that weighted mean to compute a mixed representation of these slots, which is then fed into a small render MLP that outputs the color. And as you can now see on the right, the result of this is that we not only get a 3D reconstruction of the scene, but we do also get a decomposition into objects in a completely unsupervised fashion. And what's more, that's even a decomposition that is 3D consistent, as you can see. It doesn't change or jump around, but the decomposition here encoded as colors is actually very much 3D consistent where the object is. And I found this quite surprising, to be honest, because this data set is very challenging. We tried running just normal slot attention on this data set. We tried running the scene representation transformer that you've seen without the novel view synthesis objective on just reconstruction. And we weren't able to get anything that resembled an object decomposition. It went into one of a few failure modes. But OSRT is quite stable on this and produces pretty good object decompositions for this challenging scene. Yeah, like with our slot attention models, we can then also do some editing, remove the slot that corresponds to an object, and see that it will correctly reveal the objects behind it, and we can introduce a slot from a different model, and it is appropriately inserted into the scene. Yeah, okay. So I wanted to summarize a little bit what I wanted to stress and think are the main takeaways. Novel view synthesis is a surprisingly powerful training objective. And I'm actually coming to think that 3D structure is not complicating the task of object decomposition, but might actually be helping it. Another point of a data point for this is Thomas mentioned before that Savi++ uses depth prediction to get the nice Waymo results, and depth prediction is also quite close to 3D using 3D information. So novel view synthesis and depth prediction, I encourage you to consider these as training objectives if you're interested in object representation learning. I also wanted to highlight that a trained encoder instead of optimizing for each scene. And a light field decoder are actually, they can provide an efficient way to do 3D scene representation. And our model can, for example, render these 128 by 128 videos on a single GPU in real time. And surprisingly, to me still, this model is 3D consistent, despite a rather weak 3D inductive bias. The nerf inductive bias is much, much stronger. And there's other models that have much, much stronger inductive biases. But this learns a 3D structure and a 3D consistent decomposition of objects, even with these weak inductive biases. Of course, there's still some limitations and open questions. This model still requires some pose information for training. It currently assumes static scenes, and we don't currently know how we would go about disentangling time and space if we wanted to do that. And it is also not entirely clear how OSRT actually handles object pose. So we can remove and add object, but is there like a pose where we can rotate, shift individual objects to do some physical reasoning, to do some interaction, and to reason about these things? That is not clear at the moment. Okay, and I think with this I'll end and open for questions.
Okay, thanks for the talk from Klaus. Here is a question from the audience. Like, do you have some instance segmentation loss during the training? I think, yeah. And the second question is like, is there some intuition to use light field representation with the transformer structure together?
So first of all, we have no instance segmentation loss. Similar to the slot attention models that Thomas presented earlier, the instance segmentation is purely a result of the structure of the model that does some clustering on the scene representation, and then the decoder being structured in a way that encourages decoding each slot separately. And the combination of these two things, we find, if set up correctly, and especially with novel view synthesis, seems to lead to quite stable decompositions into meaningful objects of that. I'm not sure I know what the second question is getting at. Do you think it is about explaining how it works, or an intuition for why we did this in the first place?
Yeah, I think the audience want to know like why, for example, you use them together. Is it like some reason that you find like in the experiment that like this light field representation need to have like transformer to make it work? Or yeah, maybe you have alternative to do that. Yeah, I think maybe they want to know that. Yeah.
Yes, the transformer somehow transformers are magic. I cannot really explain it. Transformers somehow work surprisingly well for this kind of thing. We have some thoughts and intuitions, but I can't back any of this up with hard data. But what I can definitely say is that we've tried quite a bunch of other parameterizations, and it seems like the attention mechanism is very good at establishing a connection between the parts of the scene that are relevant and the pixel that is currently needs to be reconstructed. So we've also looked at the attention maps later, and you actually then do see what you would expect to see, namely, if you have a pixel that points at, I don't know, a car, you'll see in all the input images the tokens being attended to that correspond to that car. So the transformer is somehow able to internally construct a representation space where it can then efficiently query and retrieve the right kind of information for every ray. It would be interesting to understand exactly what it learned to do. But at the moment, all I can say is that we find this to be surprisingly effective, and we couldn't find a different architecture that performed as well.
Okay, yeah, thanks for the answer. And maybe I have another question, like from the results, I saw that like you maybe only use like 5 or maybe less than 10 images for reconstruction. So have you tried like even more? Because like for the nerve things, like they may show more, I mean, like high resolution images, but in your case, it's somehow like blurry. So have you tried like more images, whether it improves the performance?
Yes, we have. Not much more. So typically we do either 3 or 5 images for our experiments. The reason is that we want to use this for representation learning for scenes. The novel view synthesis for us is a training objective first and foremost, and the blurriness itself is not that big of a problem because we are not interested in producing high quality renderings. But you are right; it is blurry, and quality does improve with the number of inputs, even if you only increase them after training. So if you train with 5 images and then you give it 10 during test time, quality does go up. But also the way it's currently set up, the scene representation scales with the number of input views because it's a self-attention transformer. Therefore, it also becomes slower and slower.
Okay, yeah.
If there's some time, I'm having one question. Hi, Klaus. So you list on the limitation slides that one of the limitation is that you are assuming the camera poses are given, but for the light field transformer, because you are removing this recasting, why in that case the camera views are still necessary? So can you just remove the camera poses?
Not entirely, unfortunately. So we don't need the camera poses for the encoder at all. But what we need to do is we need to somehow communicate to the decoder what target view it should construct, right? Because we want to then do a mean squared error with the target view. So we have to somehow have a way to ask the transformer decoder the right question. We have to ask for a particular view. And the way we do this right here is that we mark one of the input views as special, and we then tell the decoder to say, please give us the image that is the same perspective as the first input, but the camera shifted a bit to the right and up, or something like that. And that way we can ask for the right view, and then use that ground truth view for the loss, for the training loss.
Then in this case, you only need one global kind of scene coordinate frame, right? So you only need one ground truth camera pose for one image, right? You don't need the poses for the other images.
For two images, for one input image and one for target image, so that we can have the relative pose between the two. That's the one. That's the one information we need. That is correct. Yes.
I see. Thanks.
Okay, like thanks again for the talk from Klaus, and we will move to the next speaker. The next speaker is the recorded talk. It's from Professor Stefano Soatto. He is a professor in the Department of Computer Science at UCLA and the Vice President of AWS AI Labs. He received his PhD in Control and Dynamical Systems from the California Institute of Technology in 1996. His general research interests are in computer vision and nonlinear estimation and control theory. In particular, he is interested in ways for computers to use sensory information, for example, vision, sound, touch, to interact with humans and the environment. I think the technician can help us broadcast his recorded video. Thanks.
Hi, I'm here to talk about visual objects, their emergence and representation. Before I do so, I'd like to acknowledge my collaborators whose work I will connect through the arc of this talk. Now, when thinking about visual objects, we think of pieces of an image we give names to. And as a reminder, while much of your brain is devoted to processing visual information, about half of your cortex if you're a macaque monkey is shown here in color, language emerged very late in the evolutionary tree. Does it mean that visual objects are a concept restricted to humans? Well, not necessarily. You may argue that cats can reason, and plenty of YouTube videos will illustrate that. And similarly, dogs can talk, as Gary Larson pointed out in the far side. Nonetheless, if language was essential, then visual objects would be restricted to a relatively small branch of the phylogenetic tree. Now, you could argue that evolution is irrelevant. We didn't build the airplane by imitating birds, at least not very successfully. And while language appears at the end of the evolutionary tree, once we have it, we can work backwards and use it to facilitate the representation of objects. So that's certainly a valid viewpoint. But even if you take that, it's worth reminding that language, which is a human construct, so its complexity cannot exceed the union of the capacity of human brains or the corpus of written text. Apparently, that requires a very small capacity to be represented, about 1.5 megabytes in humans. Contrast that with the complexity of the physical world, which is effectively infinite. When you look out the window, you can see all the way to the moon. With this context in mind, let's start our journey through visual objects. There is a rich literature on the topic, but a few attempts at the definition. And of course, the definition is implicit in the method or the benchmark, and it basically boils down to subsets of pixels in an image that somehow relate to other pixels in different images to which humans have attached some label. And related could be measured by similarity, measured by, for instance, linear product of some function phi that could be implemented by deep neural networks and maps it to some vector space. And close could be to the average of objects that have the same label in a finite training set D. Okay. But if that's the case, does it mean that there cannot be visual object without humans, without language? I think you'll be hard-pressed to argue that the dog does not have a concept of bone in his head, and that is manifest visually. Okay, you could say dogs have language, but what about dinosaurs? Of course, we don't know, but it's unlikely that dinosaurs went extinct because they did not have enough annotators. So the first point I would like to make is that visual objects exist in the scene, not in the image. They're just manifest through the images, but there are no objects in images, just pixels. This is not a new idea. In the 50s, Gibson talked about detached objects as layout of surfaces surrounded by the medium. And those are relevant because you can grab them, eat them, and so on. But since you don't see many objects floating in midair, a weaker notion introduced in 2012 was that of a detachable object as a layout of surfaces partially surrounded by the medium. And that is relevant because relative motion triggers occlusions, and occlusions are manifest in the image, but they're informative of the topology of the scene. It tells you whether two nearby points in the image are actually neighbors in the scene. And they can be arbitrarily far. You look out the window and one pixel sees the moon, and the nearby pixel sees the window frame, right? So how does this definition impact the way we learn objects? Well, for once, portions of the scene that cannot be detached are not objects per se. They may be images of objects, for instance, painted on the ground, but a properly designed system bootstrapped from blank slate should find things like the car that sticks out of the ground, but has no basis to find the girl, unless it has seen girls sticking out of the ground before. So here we're talking about a primordial system where that starts from blank slate, like a deep neural network before you start training. But there may be some architectural biases and other inductive biases. So objects exist in the scene. And the second point I would like to make is that you do not need labels or names or interpretations or semantic to discover or to detect them. This is also not a new idea. Bela Ulesh in the 60s made this point compellingly by removing from the images all their pictorial content. So there is nothing to understand or interpret in the images, but as soon as time flows, you can clearly see objects emerge, whether or not you have names for them. Okay, you can see here the importance of occlusions again. Of course, once things move and you detect them, you can then store them in memory and then retrieve them in the future, even from a static picture. And that's the idea behind dynamic static bootstrapping that I will come to later. And here there's no supervision but time. But I argue, in addition to motion being fundamental, I also argue that there's an independent reason for the necessity of motion. So if all you see is different images, each of a different scene, since the scene is infinitely more complex than the image, you cannot possibly learn that there even exists a scene. You can just capture patterns and regularities in the images. But then again, there are no objects in images, just pixels. And again, things do not need to keep moving in order for you to see them, like the dinosaur visual system. Once moved, you can learn a model, and then you can use that to detect them in static images. Next, I'd like to turn these ideas that objects exist in the scene, that they need to move, that occlusions inform the partition of the image based on the topology of the scene, into variational principles that you can use for learning. Okay. And also later, I would like to ask the question, well, since objects exist in the scene, is there a true scene? Is there a physical scene? What is that? Can I learn that? And how? And do nerves have to do with that? So the first concept I'd like to present to you is this idea of contextual information separation, which was introduced by Yang and Loquecho and other in CVPR 2019. So imagine you have an object, for instance, the blue square, which occludes part of the scene, let's call it the background, everything else which is not the object, its complement. If you have seen scenes like this before, you could hallucinate what's behind the occluder. Okay, this is a transductive version of this called inpainting. You use the pixels outside the blue region to fill in the blue region. Let's say this is not the true object. And so you would imagine, mostly yellow and blue. But let's say that this thing is not the true object, but just your hypothesis of the object. And let's say that here's a different hypothesis for the object, okay? If this is your hypothesis, then you will do a much better job at filling in not just hay and sky, but also the zebra and all, right? And similarly, if this is your hypothesis for the object, you could fill in the background with a zebra, and you will do something. But if I give you this hypothesis for the object, you will do a much better job at completing the outside, right? So different hypotheses will yield different quality in the reconstruction of the segment of an image given its complement, okay? And the hypothesis that gives you the worst possible reconstruction is the one that makes the foreground and the background uninformative of each other. They're independent in some sense. And so those are the objects. So once projected on the image, they make the inside of the image as uninformative as possible as of the outside, and vice versa. Okay. So concretely, if this is the hypothesis, you can reconstruct its complement pretty well, right? It looks plausible. Okay. But if this is the hypothesis and it coincides with the boundary of the object, now your reconstruction doesn't know anything about blacks and whites, and it will reconstruct with blue and yellow. Okay, so this concept translates naturally into an adversarial loss function where an inpainter, for instance, implemented by a trainable module or a deep neural network, tries to fill in the complement as well as possible, while the region is chosen so that the reconstruction is as bad as possible. So here is U is any function of the image, for instance, the gray level or the color values or the optical flow or a histogram of filters. And this is a mask that masks the inside. And so you're going to try to explain the inside using the outside and explain the outside using the inside, normalize somehow. And you're going to optimize this by trying to inpaint as well as possible. And at the same time, trying to make the inpainting as poor as possible. And by doing that, you should converge to the object. Okay. Now, there is an information theoretic interpretation as the principle looks for regions that are as uninformative of their complement as possible. And this is called the contextual information separation principle. And it can be applied to any function U of the image, for instance, grayscale, color, optical flow, histograms of statistics, your choice. The first term tries to explain or compute the entropy of inside a mask M given the image or the function of the image outside, normalized by the uncertainty inside. And the second term tries to do the same for the complement. Okay. Now, for those of you who remember it, this approach is reminiscent of the classic Mumford-Shah functional, but it's backward. Mumford-Shah tries to explain the inside of a region of an image using only pixels inside that region, and so for the outside. Now, the obvious solution is that phi is the identity. So you need to enforce regularization, like smoothness of a statistic phi or of the boundary. Here, we do the opposite. Instead of trying to model a region as well as possible using pixels inside that region, we try to model the region as poorly as possible using only pixels outside that region. Obviously, you need memory to do that. Okay, so you can think of contextual information separation as the inductive version of the Mumford-Shah functional. The advantage is generalizability. Whereas in Mumford-Shah, for every new image, you have to solve an optimization problem anew. Here you do it once during training, right? At that inference time, you just feed forward, you compute a function. Now, another interpretation of contextual information separation is the visual analog of masked autoencoding that's popular in languages, except that here the mask is the object of inference rather than a manually concocted occluder, as in self-supervised learning. So in language, the boundary of objects and the object of inference correspond because they're only discrete characters, not shapes. And here are some examples and numbers that show that CIS works when applied to motion statistic, that is when U is optical flow. But I find it more useful to consider when CIS does not work. Okay. For instance, if you try to apply directly to the pixel in a static images, like the random dot stereogram of Buresh or this mountain goat, it cannot work because there is no separation between objects and the background, often by evolutionary pressure. Of course, motion can help, but even in this case, the camera is moving. And more importantly, the temporal reinforcement from repeated observation, knowing that you're looking at the same scene, should help. And this is the key idea of this tab. You start with a clean slate, and as soon as you detect objects, you can feed them to a time-supervised detector that trains a static module that then improves the inpainter inductively, which then improves the discovery of objects until you've captured the world, or at least the world that at some point or another stands out or moves. And here's an example, but much more work is needed in this area with many contributors to this progress, including in this workshop. Another important aspect of this tab and modeling objects in the scene is that you can integrate multiple sensory channels. I've shown the case of motion and color for this tab, but you can also have vestibular sensors like inertials, accelerometers, gyro, magnetometers. Then in that case, you can maintain a metric representation of the world. In this older demo that was shown live at CVPR 2017, Jingmin Dong, Konstantin Soatto, Shahan Fei, and others have shown that even though visually indiscriminable, a proper object representation can distinguish between a toy car and a real car, since they have an indirect measurement of scale from visual inertial odometry. Okay. And the same goes with occlusion. Even when not visible, previously seen objects are known to persist. And so you can retain them in memory and predict when and where they will be visible again. So in this case, the chair becomes occluded by the monitor, but you know it's still there. And scale and occlusion are the two most challenging phenomenology in image formation. So visual object representation should account for them in a fundamental way. Now, I think that some of these ideas I talked about should be fairly uncontroversial. Objects in the scene, they are primed by motion, they can be bootstrapped and then represented statically, multisensory validation, have persistence and scale and so on. But I have used the term information and informative in reference to images that are measured or training data, which sits in memory. And I think it's important to know that when you try to be more precise about what information means in the context of inductive learning, things can get very tricky. So I want to spend a few minutes giving you a sense of what's behind the word information, as I say. So as a reminder, in communication, information is a property of a distribution of random variables. An anecdote is that Robert Fano, talking to a group of us gathered at a workshop, reminded us that Wiener once walked into his office where he and a few fellow graduate students were working and stated nonchalantly that information is entropy, and then left, which left everybody puzzled, and so they had to go look into it, and that the rest of the history of information theory. But here, there are no random variables. There are images and there are data sets. They have zero entropy. Now, whatever information means for an inductive system, it's in the data set. There's nothing else known to the model before you start training. And after you're done training, whatever information was in the data set is now in the weights of the trained model, which are also fixed, typically. Okay. And so the fact is that there is no random variable. You have one data set and one set of weights. So technically speaking, there's zero information. And even if you treat data set and weights as random variable, because a trained neural network is a deterministic system, it has infinite differential mutual information. So either way, classical notions of information from communication theory don't really make sense in the context of inductive learning. But the notion of information that the weights, which is what's left after training, contain about the data set, which is what you have before training, appears everywhere in inductive learning. And this is an example in the generalization bound. So you would like to be able to say that your model works well for test data, which you haven't yet seen, so you cannot compute this number, the test loss. But you can compute the training loss, which is what you optimize, and you would like to bound the test error with the training loss plus something. And that something, in a variety of bounds, this is one of them, shows up as the information that the weights contain about the data set. Okay. So as I said, for a deterministic trained neural network, this number is infinity. So what these bounds tell you is that the test error is less than the training error plus infinity, which is not very useful. Okay. And so let me tell you another way in which this notion of Shannon classical mutual information doesn't make sense for trained models, even if you could compute it, even if you had a distribution of data set and a distribution of weights. So take your trained deep neural network. It has a bunch of weights that are sitting in memory. And now take the data set and append each datum to a weight. Okay, typically you have more weights than data, and so you can just store your entire data set after the least significant bit. So now the information in the weights, as their coding length measured somehow, has increased, okay, by the volume of the data set. But do you expect that your trained network will work any better on test data? Probably not, right? So this information, whatever that means, is really inaccessible. You cannot do anything with it unless you see the data again, which you will not by the inductive hypothesis. So what is the quantity here that you should put in the, for instance, generalization bound that you can actually compute for a trained network with a fixed data set and after it's converged to a fixed set of weights, okay? Now, it turns out that Shannon gave us some hints on how to do that, at least for communication. And so the idea was that he was trying to measure the entropy of the English language. So he took a, let's say, a segment of text, and then he added noise. You can think of removing, if you want to think about masked autoencoding, some letters or words, and then ask people to fill in the words, okay? And if you can fill in the words exactly 100% of the time, well, that word did not contain a lot of information. You might as well not store it or replace it by noise or empty, okay? But if a word or a character was so ambiguous that different people guessed different things, then you would want to store that with many bits and use that to compute the entropy of the English language. Now, for communication, that's easy because the task is the same as the data set. Here comes a message and you want to transmit it and replicate it at the destination. For us, this is different because we're not interested in the data. We'll never see the training data again. We're interested in data we haven't yet seen. And so this is another ingredient comes to play here, which is the performance you desire in the task. Okay, let me give you an example. Suppose that your task is to classify airplanes from cartoon characters, okay? Binary classification, let's say the data set is balanced and so are training test samples. So if you're okay with 50% performance, then you don't need any information stored in the weight. You just say cartoon characters every time and you're wrong 50% of the time, okay? And even if you're okay with 75%, let's say, error, you could just store a color histogram, and if there's a lot of blue, you say airplane, and otherwise you say cartoon character. And that that representation is robust to noise. So even if you perturb the data a little bit, you still get 75% correct. But if I now say, 75% is not good enough, I want 99.9% correct. And by the way, perturbing the data or perturbing the model is dual, at least in the first layer of deep networks. But if, again, I want 99.9% correct, now I have to account for the fact that there may be planes with cartoon characters painted on them. And the moment I perturb the data or the model, I will make errors, okay? And so the representation I need is substantially different, okay? So how do I turn this into a measurable expression for the information in the weight, the accessible information in the weights, okay? And here's the idea, which you can find in a paper titled Where is Information in a Deep Neural Network? So you start with a deep neural network and train it to converges and get a set of weights. It doesn't matter how you train it. You could have been trained with stochastic gradient descent, deterministic gradient descent, really doesn't matter. You get a set of weights, okay? Now, take those weights and perturb them however you want, okay? You add noise to them, for instance, sampling it from a certain distribution with a certain covariance along all directions. And again, this is your choice. This is a feature, not a bug. You pick the distribution of noise, and that's essentially the unit by which you measure information. And also you pick a threshold, okay, a performance threshold. That's again a feature, not a bug. It's a control parameter you have. So now, the amount of noise that you can add to the weights that keeps the training loss, which you can measure, below your threshold tau, is obviously information variability that is useless to you because the network doesn't see it. Okay, it's hidden behind the function that computes it. And so this is the irrelevant information or the useless information. So it's the maximum amount of noise you can add, which you can compute because you choose the noise distribution, that doesn't damage the training loss, which you can measure. Okay. Now, whatever information was in the dataset before you started training, that's a constant, you don't get to touch that. That would be, the difference from that would be what's left. That's the residual information which is accessible by the model. So this is the definition of accessible information. It's what's left after you remove or after you add noise to the point where your network doesn't see an effect. Okay. Now, this is an optimization problem constraint. You can turn it into its Lagrangian form, and the second order approximation of that tells you that this is related to the log determinant of the Physion information matrix. And that has a lot of connection also to stability of training, curvature of the loss landscape, and other things that I don't have time to get into. But the bottom line is that the definition of information in a trained network has associated with it a Lagrangian. And this Lagrangian is a variational principle that you can use for training that will yield maximum generalization. Okay, and this Lagrangian is called the information Lagrangian. It was introduced in 2018 in this paper, Emergence of Invariance and Disentanglement in Deep Representation. It looks like an information bottleneck, but it's not the information bottleneck that's talked about in papers about the information bottleneck. That pertains about the activations of the network given test data. This pertains about the test training loss, the data set, and the weights. Okay, and again, to second order, this is approximated by the Physion information. And of course, you don't need to technically add noise. Okay, conceptually, you can just compute it. But the beauty is that SGD actually puts noise there for you during training. So all you need to do is you need to store the last gradient vector before you stop training. Okay. So what is new here? So there is a definition of information that can be measured by the size of the maximum perturbation that you could apply to the weights. You don't technically apply it without incurring a training cost. This is well defined, whether or not you have deterministic model or stochastic model like a Bayesian neural network, whether it's trained on a single data set or on a distribution of data set, whether it's trained with stochastic gradient descent or deterministic gradient descent. Associated with this information, there is an inductive principle, which is the information Lagrangian. And this relates to Physion information and is computable for real-world deep networks, not in the trillions of parameters, but in the many millions, not just toy problems. And this also yields generalization bounds that are non-vacuums. So hopefully you can see a rich world of exploration around the issue of memory, information, knowledge, and transferability that emerges simply from properly trying to define information that the present data contains about the scene. The scene bit manifest, for instance, by a training set of data of the same scene. Okay. Now I want to come back to the last point I mentioned in the introduction to this talk. Since objects exist in the scene, the real scene, not images of the real scene, can we actually learn the true scene, the real scene? And what does that even mean? And things get interesting pretty quickly. So the first point here to notice is that physical objects live in the continuum. Now, whether the scene is, that the world is infinite, whether it's continuous or discrete, physicists haven't told us that yet. But I can certainly move in the continuum. And even if I sample images on discrete time intervals, those intervals can land on a dense trajectory. And so I can generate every possible image, even with just one particular scene and more. Okay. Now, of course, objects can only be experienced through observation of finite data and can be stored with finite resources of memory computed over finite time. And so the question of reality is really, can we represent in our head or in the weights of a deep network, scenes, which are essentially infinite objects, with discrete entities. You can call them symbols, you can call them programs, okay? And can you represent them in a way that you really understand them, not just approximate them, okay? But can you represent the essence of an infinitely large scene with finite memory, infinite time with finite resources? Okay, this is the classical signal to symbol barrier problem. So we put a few ideas in a paper recently, you can find it on arXiv. And the first point this paper makes is that in terms of abstract concepts, which are things that are represented inside your brain, that could have an infinite manifestation, okay? Like take, for instance, the example of pi. You have a concept of pi, and that has an infinite manifestation, an infinite number of decimals. You've never seen all of pi, right? But at some point, you get pi, you understand pi, to the point where, if necessary, you can simulate the entire efflux of digits all the way to an arbitrary point, okay? So similarly, if instead of pi, you're looking at the scene, can you get the scene? Can you understand the scene? So Gold in 1967 taught us that a deep network, well, it didn't talk about deep networks, but we kind of translated into the language of networks, can actually understand an abstract concept, meaning that it can represent infinite time with finite memory, even though it has an infinite efflux of data. However, an external entity, for instance, you watching the deep net, cannot know when such understanding has occurred. Okay. For instance, in the case of pi, you could train the network with the digits of pi up to a point, and you can ask the network to extrapolate, but at some point it will have to stop. And how do you know that the network will not get it wrong from that point onwards? Okay. So the second point we make in this paper is that physical objects are abstract concepts. There really is no difference between pi and a physical scene. Okay. However, bad news is that a feed-forward architecture, no matter how big, no matter how trained with, no matter how many data, cannot understand physical reality. Okay. In fact, a CNN cannot even classify even from odd numbers beyond a certain size. Okay. And a multilayer perceptron, for instance, on Earth, cannot fundamentally understand physical reality. Okay. Now, for an architecture that has some type of recursion mechanism, even implicit in the data, like in a transformer, you can understand reality, but your understanding of reality needs to be constantly validated. Okay. And that requires ability to control the data acquisition process, to interact, to intervene in the environment. Okay. And this is the interaction part that I haven't elaborated in. And this is not just an academic exercise where you think about abstract concepts and pi, but there are real implications in authentication. We live in the age of deepfakes, metaverse, and other things. And so the bottom line of this talk is that the signal-to-symbol barrier can be overcome by a trained deep neural network who can interact with the environment, but we humans cannot know when such understanding has happened. And I'll leave you with a few references for those of you who are interested, and feel free to reach out to me if you have any questions or comments, and I'll be happy to respond. Thank you.